Hello guys, welcome to another session of Mate Math. I hope you guys are doing good. Um, Today in this video, we are going to look at how we can integrate square root of tan x and also cube root of tan x. And as you can see, integral of square root of tangent x dx versus integral of cube root of tangent x dx. This one is what? Square root, and then this one is what? Cube root. That is why I did it this way. This one versus this one. Who wins? This or that? Which of them is more? Which of them is more easy to integrate, or which of them is difficult? This one or this one? Well, that is why I said initially that is why I did it what this way. So whether this one is a difficult one or this one is the easier one or this, you're just going to find out at the end of this video. Yeah. The approach that we are going to use is very simple. It's one of the approaches that we have been using. This one here and then this one here doesn't require any unique approach to solve. It's just one of these normal approach that we have been using in solving our normal or integral problems. Okay, so integral of square root of tangent x is not something that should let you think, let's say, critically. Though there are some other approach that we will use, but as for that one, it's not that unique, it's not that difficult. Yeah, it's not that difficult. So this one does not require any unique approach before you get answer to what? Integral of square root of what? Tangent what? X. The approach that we use to solve this one is going to be the same approach that we are going to solve this one also. But just that with this one, as we are solving it, you see that we will use a way or maybe a method which is a little bit different from what we would apply to this one when we are solving this one. Okay, so yeah, I said I want you to know the reason why I did this way. Integral of square root of tangent x dx versus this one. When we are starting our solution to either this or this, we are just going to use the same what approach, but that does not mean we are going to get the workings for this one is going to be the same thing as well the workings for this one. I said the same approach, but there is going to be a little different in the workings of this and then that of this. How you approach this one as the workings goes on will be a little bit different from how you approach this one. So I believe that at the end of this video, you'll be able to know the difference between this and then that in terms of what the workings. Well, with this the little that I've just said, you can pause the video and try your hands on, but though I haven't mentioned the approach that we are going to use, but you can pause the video and try your hands on with your own, using your own what approach. Yeah, if you get stuck, then you just come back and watch the video. And with this one, I'll just entreat you to watch it to the very end, though it's going to be a little bit long, but if it is a little, when you are watching and you think it's very slow, maybe you can try playing it 2 times or faster. Okay, yeah. So which of them are we going to start with? Well, we're just going to start with this one. We're just going to start with integral of square root of tangent x dx, and the approach that we are going to use is what? U substitution approach. And someone may ask, how is the substitution approach going to be used? Well, you don't worry. When we start working things out, you will know how the U substitution approach is going to be applied. Well, what do you think, guys? Now that we know the approach that we are going to use, and also a little bit something little about this and this, why don't you let's get started? All right, so let's get into the video. As I said, we are going to start with this one first. Integral of square root of tangent x dx. I said we are going to solve this problem using U substitution approach. But how is the substitution going to be applied? Well, you can what do you think? Should we let U be equal to tangent x? Then we differentiate. You know, when U is equal to tangent x, the U be equal to secant square x dx. And we can use trig identity to find what is going to replace secant squared x in the U world, because from trig identities, 1 plus tangent x squared is equal to secant x squared. So if we are having secant x squared, we can replace it with what? 1 plus tangent x squared. And from the first substitution, tangent is equal to U. So wherever we see tangent, we just put U there, and that is going to give us 1 plus u squared. Then we put into the integrals and then we work things out. But when we do it that way, maybe you can do it that way, and I'm sure if your algebra is good, you'll be able to work things out. But when you do that, you're just going to get u times, square root of u times 1 over 1 plus u squared, and then du, and then the square, it will become square root of u over 1 plus, something like that. If your algebra is good, you can, solve that one. But the reason why you are not seeing the workings for what I've just said is that we are not going to use that approach. I want to stick to the approach that I'm going to use. Though I'll be showing you some workings with this one, all solutions, any workings that help me to get my answer for this question here will be all shown. I'll just show you all workings. Also, it's all workings that are required when solving this problem here. I'm just going to show you all, guys. Okay, so as I was saying, you are not seeing that work, what I just said. You are not seeing that workings because that is not what I'm going to use in this video. Okay, so I'm just going to show you what I will be using to solve this problem or in this video. Okay, so I'm just saying it should, in case if you want to omit the approach that I'm going to use and you want to go by, let's say, your own approach of, let's say, u is equal to this tangent. I just want to say something about that one, so in case you want to use it, then you know how to go by. Okay, all right, well, this one is tangent x, and there's a square root on it. If we square this one, if this one appears to be tangent x squared, then the square root will go off, and then the problem will become very simple. But what is here is not what I just said. So what are we going to do then? Well, we are going to let u be equal to the whole of square root of tangent x. Yeah, we are going to let u be equal to the whole of square root of what? Tangent x. Why? I just want to avoid any radical. I mean the square root. The first substitution that we did, letting u be equal to tangent x, we will end up getting square root of u over blah 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 times something. Okay, and I remember I said if your algebra is good, you'll be able to do it. I'm not saying you won't be able to do it. If your algebra is good and you go for that approach, no problem, you'll be able to get your answer. But if it is not good enough, then you will find yourself wanting. So we are going to let u be equal to square root of what? Tangent x. Then we will find what is going to replace the x in the u world. Alright, now let's start. U is equal to square root of tangent x. And as you can see, what are you going to do? We have to find what is going to replace the x in the whole u world. Why? Because we are moving to another world, which is not x but what? U. And with integrals. If it is not a double integral and maybe it's a single integral, there is no way you can deal with two variables at a time, provided you want to treat the other one as what? Constant. But here is the case we are doing substitution, so we cannot treat the s there as what? Constant. Okay, and it's not a double integral, so we cannot treat the dx as what? Constant. We have to find what is going to replace the dx in the whole u world. Now, how are we gonna get that? You already know, so we have to differentiate, but I'm not going to differentiate this one directly. First, I'm going to square both sides. I'm going to square both sides so that the differentiation will be easier. I'm not saying you can't differentiate directly from here. It all depends on you. When you figure out the approach, how you work things out depends on you. The most important thing is to get your answer at the end of the day. So if you do whatever blah 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 blah, any tedious calculations, tedious substitution, and you don't get the answer that is supposed to be the answer to the question, you are wrong. So make sure if you choose your whatever approach, whatever blah blah, you end up getting what? The required answer for the question. So we are just going to square both sides. Now when we square this one, it will give us what? Tangent x. And when you square this, you're just going to get what? U squared. Good. Now I think this one it's simple to differentiate. This one too is simple, but if you want to deal with complex things, then you differentiate directly from here. Yeah, I want to avoid that one and make it simple for you guys, but if you want that, it's your choice. All right. Yeah, this one is just going to be fun. You come across some things that we already know, but we will not think that we can apply or we can use them in solving integral problems. That's how math is. Yeah. So u squared is equal to tangent x. Well, this one, as you can see, is very simple to differentiate. The derivative to this one we all know, and also to this one is you all know. So when we differentiate u squared, it is going to give us 2u du, and then when we differentiate tangent x, it is going to give us what? Secant squared x, or secant x squared dx. Well, you see, we have gotten dx here, and then we have gotten what? Du here, meaning we can do change of subject. We can make the dx the subject, then you get what is going to replace it in the u world. All right. Well, secant x squared, we are having x here. I said we are moving on to u world, so we don't have to see anything like x in the u world. Everything has to be in what? X world. Sorry, everything has to be in what? The u world. So what is the value of, or what is similar, or what can we replace secant x squared in the u world? Because we can't take secant x squared in that u world. If you want to take it, this one, to that u world, you have to find something that what will replace this one, or that is equal to this one in the u world. And how are we going to do that? Well, we can do that by applying trig identities. From trig identities, 1 plus tangent x squared is equal to secant x squared. So if we have secant x squared here, we can go ahead and replace it with 1 plus what? Tangent x squared. Alright. Good. But still this one is in the x world. We can't take this one there. So what are we going to do? From the initial substitution that we did, we let u be equal to square root of what? Tangent x. And we squared both sides. And after squaring both sides, we had tangent x is equal to u squared. So if you want to find what is going to replace this tangent x squared plus 1 in the u world, it's just a matter of replacing tangent x squared with what? U squared, because tan x is equal to what? U squared. So if here is tangent x squared, it's just a matter of what? Squaring u squared. Okay? Good. So u squared is equal to what? Tangent x. I said all solutions, so there are some of them that I should have omitted, but you'll be seeing them. Don't let them make you feel bored. It's part. I want to show you everything that so that when you are solving it, and you are solving it, you know how answers for each step is going to arrive. Okay, yeah. So u squared is equal to tangent x. So this one here, tangent x squared or tan x squared can also be written as tan x all squared. I'm saying that because of this tangent x here. So if we write this one as tan x all squared, then our substitution will be perfect, because tan x is equal to this. Then we will replace tan x with what? This one, and then we get u squared all squared. Okay? Good. As you can see, this side is in u. When you come to this side, also in u. Though we are not done with this one, but this side is also in u. Just that this ds, but this ds here is not anything that we should worry of, because we can make it the subject of this equation, and then we will put it into the integral in the u world. Alright, so u squared raised to the power 2 will give us what? 2 times 2 give us what? 4. So 2u du is equal to u raised to the power 4 plus 1 dx. Good. So as I was saying, this one is in u world, and this one is just a number. We can treat it as constant in the u world, but because we don't want to see anything of x, I'm just going to make this dx here the subject of this equation. And how are we going to do that? We're just going to divide both sides of the equation by u raised to the power 4 plus 1. This one divided by u raised to the power 4 plus 1, and then this one also divided by u raised to the power 4 plus 1. Now this side, the numerator and denominator will be the same, and it will go off, and it will be left with dx. So we will get dx will be equal to 2u du over u raised to the power 4 plus 1. Alright, so this one here is the same thing as dx is equal to this, or this is equal to dx. With the equation, the left and right hand side are the same, so anyhow you write it is what? Okay. Alright, so guys, when we enter the u world, we are going to replace square root of tangent x with u. Then we will replace dx with what? 2u over u raised to the power 4 plus 1. So let's replace them. All right, this one is representing what? The square root of what? Tangent x, and then this one is representing what? The dx. Is this one times this, but multiplication is commutative, so anyhow you do it, it's just the same thing. Okay, now this times this will give us what? 2u squared. 2u squared. All right, so after the substitution in the u world, the integral has now become integral of 2u squared over u raised to the power 4 plus 1 du. Well, we have just moved from one step to another, but as you can see, even this one can be even more difficult to solve than the when we were in the x world. We thought we were moving from the x world to u world to make the problem very simple for us to solve, but here is the case. What we are seeing is even a little bit difficult than what the world that we were in. Yeah, maybe I'm saying this because generally that is what most people would say. If you know what you are going to do, this one is not something that should it's not something that you should think is very difficult to solve, provided you know what you are going to do. If you already know your algebra is very good, this one is not anything difficult. But generally, if you take the question and then the what was in the S word and then you compare it to this one, in general you will say this one is a little bit difficult than the other one. Okay, but as I said, if you know what you are going to do, if you know what you are doing, this one here is rather easier than the square root of tangent x. Yeah, you know why I'm saying this one is easier than the other one. All right, so what are we going to do here? Well, as you all know, we can put this constant at the back here and then we work on this, but we are not going to do that. Even if you put the constant out and then you work on this one, the approach that I'm going to use, you will still bring this one back to where it was. So there is no need for us to bring this one at the back here. For now, let's leave it as it is. Let's leave it where it is now. Yeah, for now we will not touch it. We're just going to maintain it there. So what are we going to do? If this 2 is not there, it could have become u squared over u raised to the power 4 plus 1. And even with that one, if you don't know what you are going to do, still it's very difficult. But how are we going to approach this one? Well, should we use we cannot factorize this one, and when we try using trig substitution, that one we also will end up worsen it. So what are we going to do? And I don't know if we can find a way to write this one as a two different fractions, of which maybe we can split and then deal with this at the end of the day. But any idea? Another substitution. when we differentiate the whole of this here, we are just going to get 3u to the power 4u to the power 3, and that one we cannot cancel out with anything here. So when we even find what is going to replace this one in the other variable word, we're just going to end up getting what? Cubed root, and that is going to worsen the problem. So what do you think? Well, this is what we are going to do. This one is u squared, right? Good. And we know something from symmetric functions. A squared plus b squared can be written as a plus b all squared plus minus 2ab. Yeah. So with that idea, we can rewrite this denominator here, and that is going to give us u squared plus 1. This one here is the same thing as well, 1 squared, or maybe 1 squared, and this one here is the same thing as u squared all squared minus 2u squared. It will be a times b, and this one is a and this one is b. So u squared times 1 will give us what? U, and times 2 will give us what? 2u squared. When we write it as that directly from here, we will end up finding the way of what? Splitting the fraction that we are going to get into what? Two different fractions. I mean, the denominator will be the same, but the numerator will be what? Different, a little bit different. So when we do that one here, it will be a little bit difficult. So what is what we are going to do? First, let's try and then reduce what? The powers. This one is what? U squared, and this one is what? U to the power 4. Let's try and then reduce the powers by maybe we can, this one is to the power 4, meaning we can bring u squared out. Someone may say, how is that possible? This one, there is no u here, so we can't factor u squared out. It's possible because this one here, we can divide this one by u squared, so that at the end of the day, when we open the bracket, we will just get this one back. Okay, so we're just going to reduce the powers by factorizing u squared out. I mean, this denominator, not this. We are having u squared here. So if we factorize this one by bringing u squared out, we can do cancellation. That is, what has come out will be the same thing as what is here, and that one will cancel out, and this denominator here will be a little bit reduced. And when it is reduced, we can apply the idea of what? Symmetric function. And with that symmetric function, what we will get will be very simple to split as compared to this one. What do you think? You don't worry. Let's start working things out, and you know what I'm saying. Okay? Yeah. Guys, just make sure you watch this video to the very end, and at the end of the day, oh, it's not that difficult as I was thinking it is. Alright? No. Integral of square root of tangent x is one of the integrals when you are solving it, because of how it is, it lets you apply the idea of what? Other areas. And when you do, it makes you think that, oh, there are some instances you can apply certain things you have learned which doesn't even relate to the topic that you are dealing with in order to solve your problems. That is why maths we learn it step by step. What you learned in maybe SHS can be applied at maybe in your PhD exams or PhD program that you are doing, particular program that you are solving, which require, who knows, this one that we are looking at SHS. I don't think SHS student will be given this question to solve, and maybe some university student, and that person might have learned symmetric function and maybe SHS math, and maybe under different topic which is not what? Integral. But here is the case, he is going to apply this idea to help him solve his problem. And that is what the importance of learning the mathematics in steps. or in stages or in levels. Okay, though this one is integral and the other one is what, maybe they didn't be symmetric fashion, but if that one can really help you solve your problem, it doesn't matter. You just apply it and you solve your problem. At the end of the day, you will never be penalized if you get your answer correct. The marker will not say because you use approach which is not under integral topic, he's going to mark you down. No, if your answer is correct, it's correct. Yeah, so that's how mathematics is. So as I said earlier in my previous videos, that with mathematics, solving problems at the mathematics requires what, application of what, other approaches to her. Yeah, require application of other approaches. When you learn, make sure in the problem that you are solving, you try applying only if it is possible. If it is not, you just stop. If it is not possible in A, maybe one day in B it will be possible. Then you just use it and you are good to go. That is the reason why you learned it. You didn't learn it because we were told to learn by your maybe your teacher, or maybe your lecturer, or maybe your yeah, you know what I'm saying. Okay, so that's what we are going to do. So first we are going to factorize this denominator here. No, this one there is no u here, but we can divide this one by whole u squared so that the factorization will be possible. So when we do that, this one will be what, u squared into bracket u squared plus 1 over u squared. Okay, and you know when you open the bracket, u squared times u squared will give us this, and 1 over u squared times u squared will give us all this one here. Okay, you see. Now let's go factorize the denominator. Yeah, factorize the denominator. This one is to remind you of what we are going to do in our next step. Good. So as I was saying, now after factorizing, you know, this one has become u squared plus 1 over u squared. And when you open the bracket, you see that this and this will cancel out to give us this one, to give us what, this one, and this time this will give us what, u raised to the power 4. So you see, it's now possible. Now what are we going to do? This one here is the same thing as what is here, so this and this will cancel out, and it will be left with what, 2, and here it will be left with what, u squared plus what, 1 over u squared. Good. Yeah, somebody may say, hey, he said we were going to see something which is very simple, but even this one, how are we going to do it? Yeah, how are we going to do it? Though there is no u squared here, though here it was u raised to the power 4, but instead of u raised to the power 4, we have gotten u squared, and then here it was 1, and then we have gotten 1 over u squared. Even the 1 we didn't know what to do with it, but how much more 1 over u squared? You see, then if you don't know what you are going to do here, actually I don't know what integral formula that when you apply will give you answer to this one. Yeah, I don't know what integral formula. Maybe some is there, but maybe I haven't seen it. Yeah, let me say it that way, because here I don't know what integral formula that when you apply it will give you this one. If you bring these two at the back here, and here is 1, so 1 over 1 over u squared plus 1 over u squared du. Yeah, when you have problem of that nature and then you integrate, the answer that you are going to get, I don't know if we have a formula for integral of this nature. Yeah, I don't know. Yeah, then yeah, I'm saying it because somebody may say we have end up making it, a little bit difficult, or maybe easier because with this we might get an integral formula for this one, which meaning integral of this one is equal to a particular answer without any further step. I mean, there is a formula for integral of this nature. To me, when you ask me, I will say, well, I don't know, I actually don't know, but they may be, but as for me, I don't know. And since I don't know, I have to find another way of dealing with it. I have to find another way of dealing with this so that it will become something that I know better. So what are we going to do? Well, here still, we are not going to bring these two at the back here. We are just still going to maintain it here. And then our focus is going to be on this denominator's position. You know, with this numerator here, we don't have anything difficult here. Yeah, these two, so we are okay with the numerator. But the problem here is the denominator. So what are we going to do? Okay, somebody may suggest that, okay, what if I differentiate this one? You know, the derivative of this, when I get the derivative of this, and at the end of the day, I just add and subtract from the numerator, maybe it can help me solve this problem. But actually, when you take the derivative of this, you're just going to get 2u and then when you differentiate this one is the same as u raised to the power minus 2, and that is going to give us minus 2u times minus 2u raised to the power minus 3, and that is going to give us 2u minus 2 over u raised to the power 3. You know, because this one is denominator's position. When we use the negative index law to rewrite this one, it will be negative, and at the end of the day, this power, instead of decreasing, it will be or rather increase. So when you convert it back, this one will be 3. Okay, so you see, when you get something like that, and we come here, you can just add 2u minus 1 over u to the power 3, and then plus, you just add the same thing back. So at the end of the day, when you add, you just get these two back. When you do that, and then you split the other one, the first substitution will work for you, but the other one, it won't work out for you. Find difficult doing it. So what are you going to do? Well, you remember I said we're just going to apply the idea of other approach like symmetric functions. It's not under integral, but if it can help us to reduce this problem, to reduce the complexity of this problem, well, why not? We can use it. So we are going to rewrite this denominator here using that symmetric function. You know, from symmetric function, when you have a squared plus b squared, it is equal to a squared, it is equal to, into bracket, a plus b all squared minus 2ab. You know, when we open the bracket, a plus b all squared, when you open it, you're just going to get a squared plus 2ab plus b squared. So if you want to get your a squared plus b squared back, what do you have to do? Just a matter of minusing the 2ab from it, and when you do that, plus 2ab minus 2ab will cancel out, and you just get your a squared plus b squared back. So you see, but someone may ask, this one is 1 over u squared, so how can this one suit what we are going to do? Remember, with mathematics, sometimes we just assume this is this, and then you apply it in whatever you are doing. Don't let this one scare you. 1 over u squared, this one is u squared, and this one is 1. Since this one is 1, we can write this one as what? 1 over u all squared. Okay, let's forget about the function being a squared plus the a squared plus b squared is just telling us that when we have two different things, you know, a and b are two different things, and they are squaring and at the same time adding, we can write it in this way. So applying the same idea here, we can let this one be a, though the b wasn't 1 over b squared, but we will just assume the b is what? This one, by writing as 1 over all u. Just don't confuse yourself with the fraction here. Just assume that the b is equal to this one, and when you apply the function where the a and b is multiplying, just multiply, and whatever you get, you just write your answer, then you are good to go. Okay, so this one here can be written as 1 over all u. Then we square it, because 1 square the same thing as what? 1. If this one appears to be more than 1, then there could have been a little bit what? Different. But since this one is 1, we are lucky. We just write as 1 over all u. Okay. So as I said, a squared plus b squared is equal to a plus b all squared minus what? 2ab. Now we are going to assume this is what? This one is what? Our a, and then this one is what? Our b. Okay, and where it is multiplying ab, you just multiply this by the whole of this, and we are good to go. Please, when you are multiplying, don't multiply 1 over u all squared. Even if when you do it that way, you will still have to open the bracket before you do multiply. Okay, good. So when we apply the symmetric function, this is what we are going to get. You know, u squared is equal to a, and then b is equal to 1 over u. You know, we were having 1 over u squared, but I said it can be written as 1 over u, then all squared. Okay, so when we do it like that, it has now suit the function, and when we apply this, what we are going to get. So this is a, and then this is b, and that is our square. That is the first part, and then minus 2 into bracket, that is what? Minus 2ab. This is a, and then this is what? B. You know, with b we just open the bracket, because at the end of the day we have to open the bracket before we can multiply. Okay, so u squared times 1 over u squared will give us what? This will cancel out with this, and that will give us what? 2. You know, here will be 1, and 1 by 2 give us what? 2. Here, because we are rewriting it, you're not just going to expand this, but actually when we expand this one and we solve this one together, we're just going to get what you saw in the other part. Yeah, you're just going to get what you saw in the other part. Okay, good. You know, when you expand it, you're just going to get u squared plus this times this will cancel out, and it will be left with 1 times 2. So u squared plus 2 plus 1 over u squared minus 2. Minus 2 and then positive 2 will cancel out. So you just get our u squared plus 1 over u squared back. Alright. Now we have applied the symmetric function to reduce the complexity of the denominator, but still is what? Nothing. Though it has done something, but not all that something, because the problem is still the same. the other one, this one is even worse than the other one. Yeah. So how are you gonna solve this one? Any formula? Still there is no formula. So even this one is even worse than the other part. We were having one here. So here we have gotten what, 2. So even this one is a little bit worse than the other one. But it's not. Do you know why? I'm going to tell you. It's not. You know, when we write it in this way, when we are splitting into 2 different fractions, it will be it will be very simple for us, because when we differentiate this one and then we add and subtract from the denominator's position, what we will get for the derivative of this will be what? Very simple as compared to what? The other one. The other one, you might end up what? You might end up, making the problem a little bit difficult, because when you split it, the first one will be easier, but the second one, you might fumble a little bit. That is why I chose to, rewrite the denominator before we do what? The add and subtract. Okay, actually that is what we are going to do, but we have to reduce the nature of the denominator into this form, so that the derivative of this one will be what? Very simple. Very simple. And another reason is that the derivative of this one, these 2 here, we should have bring it at the back here, but we should have brought it at the back here, but we refuse. And the reason is, as you are seeing these 2 here, the derivative of this one will give us what? 1 plus 1 minus 1 over u squared. We will get y in the derivative of this. So when we add and subtract, it's going to be 1 minus 1 over u squared, and then plus 1 over u squared. So you see, so instead of going for 1, which is somewhere that we don't know, why don't we just, as we continue working, split this 2 as what? 1 plus 1. Then instead of bringing another one from somewhere, we just add the one which we had from the splitting of what? This 2 into the derivative of this, and also the derivative of what? Into the derivative of this, which will be what? Added and subtracted from what? The denominator's position. So here, instead of writing plus 1 minus 1 over u squared, we are just going to write minus 1 over u squared. Why? Because when we split these 2, you get 1 plus 1. And it's add and subtract, and the part which is added, we just add 1 to that part, and then the other part which is subtracted, we just add 1 to that part, and we are good to go, which will be the same thing as well, the derivative of this one. Okay, so here we are going to, actually there is no formula that we can use to solve this problem. So what we are going to do here is what? Add and subtract. Sometimes with integrals, sometimes you have to do what we call inspection. Inspection. You have to check if the derivative of this one will help you, when you bring it in the numerator's position, and it will help you solve the problem more easily, then you just do it. Okay, so we're just going to add and subtract the derivative of what? This one to the numerator's position. Okay, you see, I wrote add and subtract 1 over u squared because the derivative of this one is what? U. the derivative of u is what? 1. And already we are having 2 here, so we can split the 2 as what? 1 plus 1, and this one is what? 1 over u squared. When we differentiate this one, we will get minus 1 over u squared, and on top here we are subtracting, so that is what? Subtract. So the first one will be what? Minus 1 over u squared, and then the other one, we have to add it back, so that at the end of the day when we compute it, we just get what? This one back. So the other one will be what? Add, so plus 1 over u squared. Then we split these two. To show the derivative of this, we split these two. So that is the reason why we maintain the 2 there. And when we split it, where this one was subtracting, we just add 1 there, and where this one was adding, we just add 1 there, which at the end of the day will be the same thing as what? This. And which at the end of the day will be the same thing as what? When you add the whole of that numerator together. This one will be all positive and negative, so it will go away and you just get these two what? Back. But that does not mean you should only differentiate 1 over u. When you differentiate 1 over u, you are just going to get minus 1 over u squared. Somebody may do that because of this u squared here. When you do that, you cannot get any reason to base on to split these two, because the derivative of this one alone is minus 1 over all u squared. It is not 1 plus or 1 minus 1 over u squared. Okay? Alright. Good. This is what I was talking about. Yeah, you see, this plus this will give us what? These two here, and it will become the same thing as well what we were seeing before this part. Alright, good. So here we are going to split these two as what? 1 plus 1. You're just going to write as well 1 plus 1, and 1 plus 1, we will add 1 to this and also add 1 to this, because at the end of the day 1 minus 1 over u squared plus 1 plus 1 over u squared will give us what? These two here. Alright? You see, though you might think we are worsening the situation, but we are rather what? Reducing what? Its difficultiness. Yeah, I said if you know what you are going to do, each step, the subsequent steps that you are getting are the easier ones and not the difficult ones. But if you don't know what you are going to do, the original question, the original one will rather be what? The original will rather be the easier one to you in the subsequent steps. Yeah, if you look at the original one and you compare it to this one, you will say, sorry about that language, that's my local dialect. Anyway, you will say, the other one was even single, but this one, look at what we are, what I've just end up getting. The other one was even simple to deal with as compared to this one. Yeah, what is this? But if you know what you are doing, every subsequent step is what? More easier than the original one. The subsequent step are just a means of what? Reducing the original one. Yes, the original one, but we are just what? Reducing it bit by bit to what we know better, so that we can integrate. And I hope you know that the reason is there is no formula for integral of square root of tangent s, or integral of this one, or maybe the other steps. If it appears that we have a particular formula for one of the steps that we had, we could have just paused and just use the formula and then get right our answer and we are good to go. But here is the case, we don't have any formula, so we have to waste time of going through the subsequent workings just to make the problem what we know and then integrate it. This one is something that we know, but in terms of integrals, I don't know what formula, and I don't know I don't know what formula that you use to get answer to this one, unless you work with what further. All right. So as you can see, when you open the bracket, this and this will cancel out, and this plus this will give us what 2, and it will be the same thing as well, and it will be the same thing as either this one or what the original one. All right. So what are we going to do now? Remember, with mathematics, application of other areas was accepted. So we apply the idea of symmetric function to deal with what the numerator. Now here we are just going to apply the idea of what like fractions. A over b is equal to A over b plus c over b is equal to a plus c all over b. Like fractions, when the denominators are the same, we just add or subtract what the numerator. So when we have a plus b all over c, and you want to split it into what like fractions, because it is having what a single, if you want to split it to what like fractions, what do you just do? Just give it what one denominator, so it will be a over c plus what b over what c. All right. So yeah, somebody may say I will use partial fraction. Even when you use partial fraction, you're just going to get the same thing as that. All right. When you use partial fraction, you're just going to get the same thing as that. So there's no need. All right, let's continue. So what are we going to do? We're just going to split this one into all like fractions. Why? Because since this one is adding, we assume that, and since it is adding and all of them are having one denominator, we assume that both of them were having the same denominator before adding or before this step. Yeah, let's take it as that. So we're just going to split into like fractions by writing this one over the whole of this, or plus this one over the whole of this. You know, when we add it, we're just going to get this one back. Okay, I hope you are not confused. Good. Now let me make something clear here. Though I believe that I'm not the first person to solve integral of square root of what tangent x dx. No, I'm not the first person. I know there are other lecturers, the other people who have solved what I'm solving today with you. So the approach that they used to solve maybe will be the same thing, but maybe when they reach here, how they solve it was a little bit different from what you are going to see here in my video, and that is what I'm going to hammer on. The reason is that when maybe I don't know, maybe some of you might have watched a video on this question before even this one. So when they reach here, they will not after doing the add and subtract, when they are going to split in the next step, as you are going to see here, they will not write the same denominator for this one and then this one, because when you write this one over this plus this one over this, the derivative of this one is not what is here. So you remember the other part, I said that the derivative of this will only work for the first fraction, but for the second fraction it won't work unless you do other workings. So when they reach there, they will not waste time of doing what I'm going to do after this part. And the reason is what I'm saying. The derivative of this one is not this, but though in my solution here you will see that the other fraction, it is this one over this. The reason is that to avoid confusion and to make it the solution very simple, we know that when you have two different fractions, when you have two different like fractions and you add them, all of them get the same denominator. And when you split it, all of them also get what? The same denominator. So if I have written it this way and I'm splitting it, first I have to show you their like fractions before I proceed. But they will not show you the other, or they will not show you the like fractions, but rather they will skip that part and then show you the next step, which is giving this one what? A different denominator. Why? Because the derivative of this one is not what is here. The derivative of this one is what? 1 minus 1 over u squared. So if you write 1 plus 1 over u squared all over this, and then you try to do substitution to do cancellation, it won't work out, because when you differentiate this one, it will give you this. So they will rewrite this, the whole of this denominator, so that the derivative of what is going to be here will suit this one in their next step. But I'm not going to do that. Is this the same? But I remember I said all solutions, I'm showing you everything. So here, maybe if you have watched a video on that, it's just the same thing, but I'm showing you everything just to make the understanding very, 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 very clear. How and why the denominator of this one what changed. It was this state before they change it. Okay, when you are very, very, very expert, you don't just waste time in, with exams you have to do it that way so that you can go fast. But as you all know, as for me, I will show you everything. Okay, so this one over this plus this one over this, so that when we add it, we will get the whole of this one back. Though when you change the denominator for this one, and at the end of the day you add, the rate at which you are going to get this one will be a little bit different from the rate at which you are going to get their own. Though you get it to be the same, but the other one, you just do maybe a little bit workings before getting it back to its original state. I hope you are getting me. Alright, so first I'm going to show you the splitting aspect basing on the like fraction rule. Alright, so by splitting, good, that is what I was talking about. If you want to go back to where we were having the two, it's a matter of adding the two together, right? This plus this will give us what? This will cancel out with this and you just get our 2 back. This one here is same thing as this one here, so you just write one denominator and you just get 2 over the whole of this, which is the same thing as what you saw. But if I change this one directly from here, and with student thinking, and someone will say, what if I want to get the 2 back? Here is the case, I have changed this denominator. So how am I going to get the 2 back? You are just going to waste another time of working it out. The rate, the rate at which you are going to get that 2 back will be different from the rate at which you are going to get the 2 back from the addition of this. Whether you have to apply LCM, do the multiply, open the cancellation, a whole lot. But with this, just apply the rule of like fractions and then just add the numerator. Okay, so instead of showing you this part, they will say no, we have to rewrite the denominator. But the reason it was in this one was in this state before the change into that state that some of you might have seen, or some of you have seen in other video. It was in this state, and when we are here, we are just going to solve them separately. We'll solve this one alone and also solve this one alone. So when we are solving this, you will know why they change this one directly from here. But me, I'm just going to show you the splitting based on the rule of like fractions. Okay, so we are going to start with this, and when we get answer for this, and then we'll come back to this, and after getting answer for this, we'll put our two answers together, and I think that will be the solution to the problem. All right, we are going to call this one A and also call this one B. I'm doing that because of how I'm presenting it. Okay, you don't worry, as time goes on, you don't worry, as time goes on, maybe it won't always be like this. Okay, all right guys, so we're just going to start with this one, and later on we will come and solve this one. All right, so this one is A, and then this one is B. So starting with A. So integrating A, please, this one is A. Now let's write our A. Good. So what are we going to do? As you all know, we did this one from the idea of the derivative of the denominator. So here I'm just going to do another substitution. When we differentiate this, you're just going to get what is here. So we're just going to do substitution, and then we are good to go. Okay. All right, so let's do a substitution. So m is equal to u plus 1 over u. Now let's differentiate. This one will give us what? 1, and 1 over u. When we are differentiating simple fractions, and it's like the numerator is what? Let's say it's a figure, not what? A variable. Let me show you the fastest way. Just increase the power of what? The denominator, and after that you just negate the whole of this. If it is 5 over k, 6 over p, any figure over any variable, just increase the power of that variable, and later we'll just negate the whole fraction, and that's all. All right, and the reason is, when we want to change it from this fraction state to, let's say, in a form of to a different state of maybe base and a power, we will apply the idea of indices, which is the law of negative index. So this one can be written as what? U raised to the power minus 1. And when you differentiate, they're just going to get minus 1 times u raised to the power minus 1 minus 1. And that is going to give us minus u raised to the power minus 2. When you change it back, I'm just going to get minus 1 over u squared, which is the same thing as what I said earlier. Okay, so dm is equal to 1 minus 1 over u squared du. Now let's find what is going to replace the u. Just divide the whole of this by 1 minus 1 over u squared. Okay, and also divide the whole of this by this. All right, let's put it into the integral. All right, though we are in M, but we are seeing u, but it's because I want to show you the cancellation aspect. So here, this one is the same thing as what this. So this will cancel out with this, and it will be left with what? 1 over m squared minus 2 dm. Good. 1 over m squared minus 2. Well, how are we going to solve this problem? Well, with this one, we started with integral of square root of what? Tangent x, which has no formula. for it. But as we started reducing the problem to what we know, we have gotten to where we can apply an integral formula. Okay, so this one should tell you the reason why we did substitution. We will write this, just to make it, just to get it to what, where we know better. Okay guys, so here solving this one, there are two ways. How do I go to know that there are two ways? Meaning there are formula for this and maybe the other way, right? So there are two ways of solving this one. One, if you want to go by trig ratios, you have to use, if you want to go by the trig ratio, then you will go for hyperbolic functions. That is, if you want to get answer to this one in terms of trigonometry, this one, the answer to this one is going to be the tanx inverse of this. Or if you want to do log, maybe you can factorize the denominator once more and then do partial fractions and then take log, and that one also you're just going to get your answer. So, and you remember, maybe those who have already watched a video on this, some of the one who was doing that video, remember the person said here the answer to this one is just equal to tanx inverse. He will say, oh, you can do partial fraction, but that is to you, but he is going to do the tanx inverse. I'm doing all solutions, so I'm going to show you the two ways, so that if you forgot the hyperbolic function, when you get something like this, actually if you don't know all the integral formulas and you have not been frequently be using them, you actually don't know that there is a formula for something like this. Yeah, so if you don't know the formula, what do? You find a way to solve it. So finding a way to solve it is what? Method 1, and getting the formula is what? Method 2. So there are two ways, but I'm going to show you all the two ways in this video, so that if you forget the hyperbolic function, which is obviously that some of us will forget or will not remember. Yeah, and then also I'll show you the other part, which is what? Partial fractions and the logarithm part. All right, so two ways. First, we're just going to start with what? The hyperbolic function approach. Hyperbolic function approach. We have tan, sine, and then where we have the each one of them is like tangent, sinh, cos, something like that. When you have something of that nature and you want to integrate using trig substitution, you have to use what? The hyperbolic function approach, and there is a formula for it. Okay, and the formula is just, if you want if you want the formula for that problem, the formula is I'm sorry with this one, I'm not going to show you here, I'm not going to write it, but I'm just going to say it. It's just minus 1 over a tanx inverse of tanx inverse of a tanx inverse of tanx inverse of x over the x over a. Yeah, that is the hyperbolic formula for what? The integral of 1 over x squared minus 1 over a tanx inverse of x over a. Yeah. All right, so let's proceed. But with this one, it's going to be a little bit different. I'm just going to show you how everything is arrived. Okay, so with trigonometry substitution, we do what? We draw a right angle triangle. Okay, so with hyperbolic function 2, I'm just going to draw a right angle triangle. Though it won't work, though to some people maybe it doesn't work that way, but I'm just going to show you how this formula what came by. Okay, all right, so this is hyperbolic function approach. So you have to repeat the question and then let's move on. So let's draw a right angle triangle. We will put our m here, and remember these two here, because we are using the right angle approach, these two here, you know, when it is more than one, we have to square it. And before we can square these two, we have to put square root on it, so that when you apply Pythagoras theorem, this one we will just get it, so that when we square it, we just get our 2 back. Okay, so we will put our m here, and then we'll put our 2 here. It's not just 2 but square root of 2, and then we'll put our theta here. Okay, I'm not showing you this part because this one our focus is on the opposite and the adjacent. We don't need this one to do anything. Okay, all right, so we are taking what? Tanx, not tan but tanx. Yeah, because of, I think we are taking what? Tanx. Okay, I said I want to show you how the formula was what, how the formula came by. That is why I'm doing it this way. Okay, as somebody will just write the answer to this one directly using the formula, but I can do that, but I want to show you how the formula came by. I don't know, we got it to be the same. Okay, good. So you take tanx. You know, when you take tan, it's just this one over this. Tanx 2 is just the same thing as tan 2 is the same, this one over this. So tanx theta is equal to m over square root of 2. What is m? M is equal to square root of what? Tanx theta. Now let's differentiate. dm is equal to square root of 2 times sec squared dm is equal to square root of secant theta squared d theta. All right, so let's put it into the integral. All right, good. This times this one will give us what? This. And then when you open the bracket, this times this will give us what? 2. And this one will give us what? Tanx theta squared. Good. Well, now let's focus on this, on the denominator's position. Here we are having 2 here, there is 2 here, so we can factor out the 2. So we're just going to bring the 2 out. And when we do that, we're just going to get 2 into bracket tanx theta squared minus 1. 2 into bracket tanx theta squared minus 1. Now I think root 2 over 2 will come out, and it will be left with secant theta squared over tanx theta squared minus 1. All right, now the question is, when we have 1 plus tan theta squared, it is equal to secant theta squared. So what if we have tanx theta squared minus 1, it is equal to what? Is this one equal to secant theta squared, or when we have or is the same thing as 1 plus tanx theta squared equal to secant theta squared? You know how the other trig ratio like identity worked. I mean, 1 plus tan theta squared is equal to secant theta squared. Is it the same way as how the hyperbolic function identities also worked? The answer is I would say no, because tan 1 plus tan theta squared will not give you secant theta squared. No. And tan theta squared minus 1 will not be equal to what is here. So what are we going to do? From hyperbolic function identities, 1 minus tan theta squared is equal to secant theta squared. Please note, from hyperbolic function identities, 1 minus, from trig identities, 1 plus tan theta squared is equal to secant theta squared. So when you come to the hyperbolic own, it is rather 1 minus, not 1 plus, or not tan minus 1. No. 1 minus tan theta squared is equal to secant theta squared. So we are going to rewrite this denominator. This one is negative and this one is positive. So it is going to factor out to minus 1. When we factor out minus 1, it will be 1 minus tan theta squared. The reason why we have factored out minus 1 is that if we don't factor, is that we want to get the identity for what? This one, which at the end of the day will be this, and then it gets cancelled out. Good. Now this minus 1 will just come at the back here, and at the end of the day, you know why the formula to integral of 1 over x squared minus 1 is minus 1 over a tanx inverse of x over a. Now we'll bring this minus at the back here. And as you are seeing here, 1 minus tanx theta squared is equal to secant theta squared. So we are going to replace this one with this, which is the same thing as what is here. This and this will cancel out, and that is going to give us 1. When you integrate 1, you all know what you are going to get. That is what? Theta. This one, the variable here is what? Theta. If this one here is x, y, p, any variable at all, the answer to this one will be what? That variable at all. Here is theta, so this one will be what? Theta. So the answer will be what? Minus root 2 over 2 theta. Alright, but what is the value of theta? What is the value of theta? You remember we let tanx theta be equal to m over root 2. So from that equation we can get the value of what? Theta. Good. So let's make theta the subject. We can make theta the subject by taking tanx inverse of both sides. Tanx inverse of this one will give us tanx, and tanx inverse will cancel out, and then it will give us theta. Then here nothing will cancel out, so this one will be what? Tanx inverse of what? This. Good. Now let's replace this one to our answer. Good. You know, when you use the integral formula, you will get minus 1 over root 2 tanx inverse of m over root 2. This one you are seeing root 2 over 2 because this portion has been what? Rationalized, and it is because of what? The workings. You know, when you write the formula and then you rationalize, at the end of the day, you're just going to get the same thing. You're just going to get the same answer. 1 over root 2. When you rationalize, you're just going to get root 2 over 2. So root 2 over 2 is the same thing as what? 1 over root 2. Or 1 over root 2 is the same thing as what? Root 2 over 2. They are all the same. So if you don't want this answer and you want to go by the formula will give you minus 1 over root 2 tanx inverse of what? U plus 1 over u all over square root of 2. You know, when we replace what we substituted this m for, I think that is going to be u plus 1 over u. So when you see that and you also see this, they are not different, they are all the same. They are all the same. Just that here, because I'm proving the formula, we've gotten this part to be what? Root 2 over 2. And root 2 over 2 is the same thing as what? 1 over root 2. You know, sometimes when the denominator of a fraction is in the form of radical, we rationalize. So because of the workings that we did, that is how come we got this one to be what? Root 2 over 2. So root 2 over 2 is the same thing as what? 1 over root 2. Okay, so it's not different. So let's go back to the u word, but m is equal to u plus 1 over u. So we're just going to put this one here. Yeah, so that integral problem, I mean, where we split the a part, when we want to use a formula for it, yeah, if you want to use a formula for it is after the substitution that you will know that there is a formula for it. Okay, so if you want to use the formula for it, that is what you are going to get. Please, I'm saying it again. When you use the formula, this part will be 1 over root 2. And because I remember I said because I'm proving the formula, I've gotten this part to be root 2 over 2. And it is the same because this one is the rationalized form of 1 over root 2. They are all the same. So when you get 1 over root 2 and then you rationalize, you just get this one. And when you get this one and you want to convert it back, it's just a matter of what? Multiply top and down by root 2. Here will give us 2 and here will give us 2 root 2. 2 will cancel out 2 and we just get what? 1 over root 2. So we just leave it as it is. They are all the same. Okay? Good. So the answer to the a part is minus root 2 over 2 tanx inverse of u plus 1 over u all over root 2. That is the answer for the a part. In terms of what? Hyperbolic identity, or in terms of hyperbolic what? Approach. If you want to go for trig approach, this is what we are going to get. What if you want to go for natural logs? Let's find out that one also. So from hyperbolic function approach, this integral This was a is equal to minus root 2 over 2 times tangent inverse of u plus 1 over u all over whole root 2. This one you can waste time of rationalizing, but when it is of this nature, you can leave it as it is. Or even here, you can choose to, I will not waste time of converting it back. Yeah, you can choose to convert this one back so that it can match with this one. But even when you leave it as this, and then maybe you are to find a value at the end of the day, after replacing the value for all this u and this, you're just going to get the same answer. What this one will give you will be the same thing as what the formula will give you. That is 1 over root 2 tanx inverse of u plus 1 over u all over square root of what? U. They are all the same. Okay? Yeah, they are all the same. And you don't worry. In our next video, to show that or to prove that they are all the same, in our next video, I'm just going to differentiate the answer that we are going to get for square root of integral of square root of 4 tangent x. Yeah, with all baby, no fears. You're just going to differentiate that answer, and at the end of the day, you will see that what I was saying was what true, even with this one or with that form, even with this or with the unrationalized formula. You're just going to get what the same thing. Okay, so you don't worry. After this video, you just watch out for that one. Okay, don't worry. You're just going to get the same thing. All right. Now let's move on to the B. I said I'm going to show you the natural log for this one, right? Okay, so here we can also use natural log to solve this one after substitution. All right, good. So the natural log approach. Please, I didn't waste time of bringing the 1 minus 1 over u square blah 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 over this, because after the substitution that we got to know that we can use a formula, and also we can use what natural log. Okay, so I'm just going to use that portion to show the two ways. Okay, they are all the same. All right, so here we can factorize this denominator, and then we split into partial fraction. This one is what? 2. We can write these 2 as what? Root 2. When you write it as root 2, then factorization will be possible, because from difference of 2 squared, a squared minus b squared is equal to a plus b, a minus b. So we are going to write these 2 as what? Square root of 2 all squared. You see, this one, when you open the bracket, it is the same thing as what? These 2. And from difference of 2 squares, we can factorize this one. And that is going to give us what? M plus root 2 times m minus root 2. We are going to split it into partial fraction. Remember, here we are having a denominator which is in what? Bracket form. So we want to get this is the single fraction for a particular 2 fractions. It was 2 fractions which were added to get this. So to get that 2 fractions, we have to use what? The partial fraction approach. Anytime you use the partial fraction approach, remember we are going back to the original fraction. So what is the original fraction for this? To get that original fraction for this, we have to use what? The partial fraction approach. Okay, so I'm just going to split it into partial fractions. Good. Here there are no powers on the variable, so there is no the type of partial fraction that we use is what? A linear factor. If this one is squared, then we will use quadratic factor for this one. Okay, but here it is what? Just m. the power is not more than 1, so we will use what the linear factor or approach. Okay, and this is how the linear factor approach works. So a over this plus b over this. Well, to get the value for a, this a and this b represent what particular value. We said we are going back to the original fraction, so this one is representing a particular value, this one is also representing what, a particular value. We don't know, it can be the same, it can be the same, or it cannot be the same. We don't have any idea. Nobody have what, an idea. Okay, just that we're just going to find out at the end of the solution. All right, so this is how we are going to find the a and b. We're just going to use the cover up rule to find a and b. How are you going to do that? You multiply this by this plus this by this, then we equate it to what, the numerator in the single fraction form. I mean, where we were having 1 over m plus root 2 and then m minus root 2. Okay, the numerator there was 1. Yeah, the numerator there was 1. If the numerator was a variable, then we equate it to that variable. If it was 5, then we equate it to that 5. Okay, because at the end of the day, both of them will get the same denominator. When we multiply it through, then the denominator will go away. Okay, so 1 is equal to the product of this and this plus this and that. So how are we going to find a and b? Well, using the cover up rule, we are going to put m be equal to particular values. With cover up rule, if you want to eliminate one and find the other, that is where we use the cover up rule. So we will put m equal to maybe a figure that will help eliminate one and then work on the other. But normally we do that by looking at the figures in the equation. Here the figures are all root 2 and then minus root 2 and then positive root 2. So we're just going to put m be equal to minus root 2 and then positive root 2, so that this one will be 0 and then we get this, and then this one will be 0 and then we get this. Okay, so we first put m equal to root 2. So when put m is equal to root 2, a will be 0, right? Because root 2 minus root 2 will be 0. This minus this will be 0. 0 times a will give us what? 0. Now we're just going to get this. Root 2 plus 2 give us what? 2 root 2 times b will give us what? 2 root 2 times b, and it's equal to 1. Alright. To get b, we divide both sides by 2 root 2. So b is equal to 1 over 2 root 2. Please don't rationalize it. You can, if you rationalize it, when you get back to the integral, you can rationalize it. Maybe when you get back to the integral, I don't think it will give you any problem. Well, but for me, I'll not rationalize it. Okay, I'll not rationalize it. The other part is because I was proving the formula. Okay, so the first value, the b value for b is what? 1 over 2 root 2. Now let's move on to let's put m is equal to minus root 2 to get what? A. This and this will be 0. times this will be 0. So minus root 2 minus root 2 give us what? A times minus 2 root 2. We divide both sides by minus 2 root 2. So A is equal to 1 over minus 2 root 2. Good. So the value for A is what? Minus 1 over root 2 root 2. After getting the values, we just put it back into the integral. Where you split it. Well, you can choose to, bring this one and multiply this. At the end of the day, you will still bring it out. So there's no need for that. So what we are going to do here is that since this one we are having 2 root 2 here, and also we are having 2 root 2 here, we're just going to bring it out. So we're just going to bring 1 over 2 root 2 out, so that this one will be what? 1, and then this one also will be what? 1. Okay. And when we bring it out, remember this part is what? This part is what? Negative. It's minus. So minus A plus B, the same thing as B minus A. So this one here is same thing as what? This. So 1 over m minus root 2 minus 1 over m plus root 2. They are all the same. Either this plus this or this minus this. They are all the same. Now here, to solve this one, we all know the answer to integral for this one. Okay, this one is not difficult. We usually split when each of the integral that we are going to deal with is a little bit difficult. But with this one, it's very simple. The answer to this one we all know. The answer to this one we all know. So there is no need for us to split again. Okay, so the answer to this integral is what? What do you think? Natural log absolute value of m minus root 2 minus natural log absolute value of what? M plus what? Root 2. Okay. Good. Alright, but what is the value of m? M is equal to u plus 1 over u. Now let's put this one back here and then here. Alright, so if you go for the natural log part, this is what you are going to get at the end of the day. You can open the bracket. When you open the bracket, nobody cares, is this one times this, and also this one times this. This one is here because this one is multiplying this and at the same time multiplying this, which at the end of the day will be the same. But that does not make this one and then this one the same. This one is different from this one, so this and this will not be 0. Here is minus and here is plus, so they are not the same. Though this one and this one are the same, but this root 2 and this root 2 are not the same. So you can neither add or subtract this one. So you just leave it as it is. Okay? Or either you leave it this way or you eliminate the fraction in this word absolute value symbol. So I'm just going to carry on to show you if you want to eliminate the fraction in this absolute value symbol, how you are going to do it. Okay, so we're just going to eliminate it by multiplying this one by this, and also the whole of this one by this, and also this one by this. Then we divide the whole of this, the whole of it by u. Okay, so this by this will give us u squared plus 1 over u times u give us 1 minus u root 2 all over u. Yeah, we have to divide it because we don't have anything. It's not an equation where this one will go and multiply something, so it's an expression. So we have to divide it by u, so that if we want to get this one back, we can easily do that, because we will just write each of them over u. Good. Now if you want to eliminate the fraction, that is what you are going to get. U squared minus u root 2 plus 1 all over u minus natural log absolute value of what? U squared plus u root 2 plus 1 all over whole u. Now if we write each of them over u, you see you will get what? The other one back. Yeah, so with this one we can apply the law of logarithm to take away the fractions, the denominator for each of them. When we have log a over b, it is equal to log a minus log b. So when we have log a minus log b, it can also be equal to log a over b, assuming the bases are the same. And as you can see, natural log here are having the same base, so we can apply that approach. So I'm just going to write this one over this using the law of logarithm. Okay, yeah, it's very long. Yeah, don't worry, as I said, it's going to be very long, but you guys don't worry. I just want to show you everything so that when you understand it and you are working on it on your own, you know what you do, you know how to go by, you will not fumble each step, you know why you are doing that step. Yeah, you know why you are doing that step, because if I just omit some and just write as this way for you, sometimes if you are trying it and you just this part he wrote it as that, but you don't know why I wrote it as that, so you also let me wrote it as that and go away. You wrote it as that, solve the problem, but you don't know why some approaches are there, or why this particular step is there. How do I even got this step? How did he even got this step? You don't know. So that is the reason why I'm showing you everything. So when you get the understanding at the end of the day and you are doing it, you see that I've understood it. So if I omit step, I know why I'm omitting it, and if I bring this step, I know why I'm bringing this step. Okay, guys, sure. So now applying that law is going to help us eliminate this denominator, and also eliminate this denominator. Okay, this over this over this over this, since this one is same thing as this one, this and this will cancel out. Somebody may say, if it cancel out and then maybe you are differentiating, then you will not get your answer back. You will get it back because when this and this goes away, it hasn't gone away. Yeah, it hasn't gone away, because here is u squared. From the first answer we had, it was u and not u squared. Here is u squared, and here too we are having u. So this one here is gone. In disguise, it is what? Here and then here. So when you differentiate it, because it is here and then here, you will get it back. I hope you are getting me. Yeah, this one, it was u plus 1 over u plus what? Plus or minus root 2. And then we eliminate the fraction, and we've gotten it to be this over this, all over this over this. And now this u will cancel out with this u, and it will be the whole of this over the whole of this. So the question is, if I differentiate it, at the end of the day, will I get what I integrated back? The answer is yes. Why? Because this and this being taken away will not affect you, because here is u and then here is u. Let's say 2. When you come here, how many u is here? It's 2. But already we were having another u there. But this root 2, there wasn't any u there. But here is the case, you have got another u. So if you take the other u which was already there, and you take the other u which was multiplied, and then when you come here, it was root 2, and you pick this u. How many u have you got? Is it not 2? Is it not 2u that are we eliminating here? That is this and this. So there's no way it's going to affect you. So it is gone, but it's not all that gone, but rather it has been included in this and then that, and also this and then that. Okay. Yeah, you see, this is what I was talking about. When you differentiate this, it's going to get what you integrated back, because that u that we took away is in disguisedly included in this one and also this one. And same thing is what applies to this and then that. Alright, so from the natural log approach, integral of 1 over m squared minus 2 is equal to 1 over 2 root 2 natural log absolute value of u squared minus u root 2 plus 1 all over u squared plus u root 2 plus 1. Remember, this and this are not the same, so it can't cancel out. Okay, good. So from natural log approach, I brought also because we have already done another way. I'm bringing this original integral because that is where we made the substitution. Okay, so this one is equal to, in terms of natural log, this one is equal to 1 over 2 root 2 natural log absolute value of this over this. If you want to rationalize this one, it will be, when you are rationalizing it, normally we consider if the radical is not subtracting, we just consider the radical only. So it will be root 2 times this one, also the whole of this times root 2. So here will be root 2 over 2 root 2 times root 2, and that will give us 4, and that will give us 2. So 2 times 2 give us 4. So when you rationalize, you're going to get root 2 over 4 natural log absolute value of this over this. So either this one or root 2 over 4 natural log absolute value of this over this. Any of them is what? Correct. They are all the same. If you rationalize it, you get here to be 4. If you don't rationalize, you get here to be 2 root 2. The other part, if you rationalize, you get that part to be root 2 over 2. If you don't, it will be 1 over root 2. Just that the hyperbolic one, we had the answer to be all negative. And from the natural log approach, we had all, though we had negative answer in it, but that negative answer has been included in the other part because of the law of logarithm. Okay, good. So the answer to this integral a in terms of natural log is what? This one here. Now let's move on to integral b. So when we get answer for integral b, we can either use this one or the tanx inverse rule. But in most cases, the lecturers will use what? The tanx inverse and ignore this one. That one is more fun. That one is, when you use it, it's more, let me say, it's more fun than, going by this approach. Anyone who sees this guy, you are sharp, you are good. Yeah, something like that. Okay. But that's why the reason why I show you both, so that you go for which of them that you think you like. You just go for one. Okay. So let's proceed to the other part. integrating b. Let me bring it. Where we splitted, it was 1 minus 1 over u squared all over this plus 1 plus 1 over u squared all over this. And remember I said when you just add it, we're just going to get the numerator to be what? 2. And remember I said some of the lecturers or others, when they are splitting, they will directly rewrite this denominator for you so that it will suit what is on this numerator's position. And sometimes when you do that, and with student thinking, if we want to add it to check if you can get the 2 back, you will find it difficult, or sometimes find it difficult, or you do a lot of workings. So that is the reason why I split it without changing this denominator here. That is what I'm going to do actually, but I wanted to show you the splitting based on the like fraction approach. We split based on the like fraction approach or the partial fraction approach. And if we didn't use the partial fraction approach and we are using the like fraction approach, we should see the two denominators being the same in the first step before we proceed to the other. Okay, good. So here we are going to do another substitution, but the question is, when we substituted another variable for this, the derivative of this is not the same thing as what you are seeing here. This one is plus, but when you come here, this one is what? The derivative of this one will be what? Minus. So this one is 1. When you differentiate this, you just increase this the power and then just negate this fraction. Plus minus will be what? Minus. It will be 1 minus 1 over u squared, which is not the same thing as well this one. So since it's not the same, what are we going to do? Should we rewrite this u? Should we rewrite this numerator so that it will suit the derivative of this, or what should we do? Yeah, that is where the approach comes in. Instead of finding a way to rewrite this one, we can rather rewrite this whole denominator here so that when we differentiate it, you will just get this one to be plus. The idea is the derivative of this one is what? Will give you this one, but minus. Here will be 1 minus. When you differentiate this, you just get this, but what? Minus. So the question is, what if I make this one minus? When I change this plus to minus and I differentiate, the whole of the derivative of this one will actually going to give me 1 minus 1 over u squared. So if I change this plus to minus and I differentiate, the derivative of this one will give me a negative answer. And that negative answer, already I'm having another negative here. So it will be minus minus and it will be plus. And when it becomes plus, it just becomes the same thing as this one. And I don't know, they just cancel out. What do you think? Yeah. So we are actually going to make changes from plus to minus so that the derivative of this one will suit or will be the same thing as what is here. But we cannot, the whole of this is the denominator. We cannot change this one to minus and then leave this one. Okay, so this is what we are going to do. We're just going to bring this plus here and then bring this minus here, and it will be u minus 1 over u all squared plus 2. That is what we are going to do, but I'm going to show you why are we doing that. At the end of the day, when you expand it, you're just going to get the same thing as when you expand this one. Okay, just a matter of just a matter of if you sometimes take your time and then just get to know what you are going to do. Okay, This one is just fun, but if you don't think it, might think it's bored. It's not bored, okay? I hope you guys are enjoying this video, okay? So if you are enjoying it, please kindly give it a thumbs up, subscribe, and comment, okay? Yeah, let me see your comment in the comment section, or let me know what you think in the comment section. Or if you also know any other approach apart from what I'm going to show you, let me know in the comment section, okay? You know, we are all here to learn, okay? I hope you are not getting bored. All right, now let's continue. All right, so note, I'm bringing note because of why I'm going to rewrite this, and you know, from others they also show you why they are rewriting this. So I'm just going to show you the same thing, okay? From the same symmetric function, when we have a squared plus b squared, it is equal to a plus b all squared minus 2ab. Now I'm not pausing here and then move on to the next step for this one, but I'm going to expand this one for you to know that this one, you expand, you just get this one back, so that when I show you the next step, which is going to reflect in this position, which is going to be used in this position, you will know why. Okay, so now let's expand this. A squared plus b squared is equal to a squared plus 2ab plus b squared minus 2ab. No, now you know minus 2ab will cancel out with what? Plus 2ab. So this and this will cancel out, and to be left with what? A squared plus what? B squared. Isn't that equal to this one? You see, it is equal to that. Now the question is, if I change what is in the bracket, if I change the operation sign there to minus, and what is subtracting, if I change the operation sign there to plus, what will happen? Will I get the same thing? Let's find out. From the same symmetric function, a squared plus b squared, will it be the same thing as, I will not make it, if I make here minus, it will be what? Difference of two squares, and that the approach that we are going to use won't work. But the approach that we are going to use won't work. So we have to maintain this same thing here, and rather interchange the position of the operation sign. The other part here was plus, and then here was minus. So as I said, we will bring the minus here, and then we will bring the plus here. When we do it that way, will it still give me this one back? Let's find out. Let's expand this bracket. A squared plus b squared is equal to a squared minus 2ab plus b squared plus 2ab. The other part, you see, the other part is even here. Here it was plus, and then here it was minus. So you see, when you interchange the position, here is the same thing. Here it has become more minus, and here it has become more plus. So still, it goes away. So you see, so when you interchange their positions, it won't affect it in any way. It's just the same thing, but it's just a matter of what? Being equivalent, not equal. I hope you understand what I've just said. If I say it's equal, this one here, in terms of this, it is what? Equivalent. But after the expansion, it will become equal. But this one is equivalent to this one because here and here hasn't been what? Eliminated yet. So it's not equal. This one here is plus. On already here we are having minus, plus, minus, so it's equivalent. So after our actual solution, that we will get to know that this one is actually equal to what we are going to get. So if you compare it from here, this one is equivalent to this one. But when you solve this one, it just becomes more the same. Okay, good. Let's proceed. So when you interchange the position, you see it will not affect it. Here the same thing here. This one and this one cancel out. When we come here, this one and then this one will also cancel out. And when they do, here is a squared and here is b squared. Is it not the same thing as this one? Let's find out. Let's find out. Yeah. Guys, is this not the same thing as this? Yes, they are the same. So it's just a matter of what? Interchange their position. And sometimes, when you do that, you just come out with something, then you test it. When you test it and it just work out, you have learned. I hope you guys are not getting bored. These workings, I just like this tutorial. Just like this tutorial very much because it's very, 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 very entertaining, and the workings and everything in it is very, very, very good because it is just helping us to broaden our mind, and also helping us to develop our critical thinking skills. Sometimes I did not just look into a book and then say and come out with this approach. When you are thinking of how am I going to do this, if this one is positive and this one will give me negative, okay, if I bring this one here and then bring this one here, will it be the same? Provided if it has given me a different answer, this idea is what? Wrong. So far as what that particular question is what? Concerned. But since this idea has just proved the same thing as this one, it becomes what? Good. And meaning we can use it. Alright guys? Yeah. And I hope you guys are enjoying the video. Yeah, it's very, very, very easy. I really like this one because we are what? Thinking. We are what? Thinking critically. We are what? Thinking critically. Okay? So in this integral here, when you are solving it, it makes you think. It makes you think. And then this thinking that we do is not something big. It is very, very something very small that we normally don't consider when we are doing certain things. These particular things are certain things that we don't take into consideration when we are doing integration. But assuming if we take these things into consideration, we will never find any integral question very difficult to solve because these certain things, these certain approaches will help us deal with it. Okay. Now, since this approach proved to be the same thing as this, we are going to rewrite that denominator, which is u plus 1 over u all squared minus 2 as this one, that is u minus 1 over u all squared plus what? 2. Okay, and I hope you know why. So this working here is showing you what, is telling you what? The why. Alright, and now you know why this denominator is here. Okay, so when you expand, you're just going to get the same thing as what? The other one. So now we can go ahead and do a substitution because the derivative of this one will give us what is here. Okay, so let's do a substitution. So p is equal to u minus 1 over u. Now let's differentiate. This one will give us 1. This one is already minus. Now when we differentiate this, as I said earlier on, just increase the power and negate the whole fraction. And again will give us a positive. So this one will just give us a plus. So du is equal to what? We divide both sides by this one. Alright. Now let's put it into the integral. Here, this will cancel out with this one. It will be left with what? 1 over p squared plus what? 2. Good. The other part, you see, the other part, it was what? Minus. It was m squared minus 2. And here we have gotten it to be p squared plus 2. You see? So, somebody may ask this question. Does it mean that this one too has two approach? The answer is what? No. Why? Because we cannot factorize this one. we cannot factorize this one. Provided we can factorize this one, then the approach will be what? 2 for this one. But because we cannot factorize this one, we cannot factorize this one, you will not have what? 2 ways. There's going to be only what? 1 way, and that is what? Taking what? Trig. So we are going to solve this one using what? Trig approach. The answer to this one is just going to give us what? Tangent inverse. Tangent inverse. Tangent inverse. But I've noticed something about students. When the figure here is what? 1, they easily know that it is what? 1. But when it is more than 1, they know that it is what? Tangent inverse. But they find it difficult writing the answer. You will just write tangent inverse, but putting in the answers, the values, p over, it becomes it becomes a problem for them. So I'm just going to show you when it is more than 1, the reason why we do it that way. Sometimes you just use the formula. X squared plus a squared, 1 over x squared plus a squared is equal to 1 over root 2 tangent inverse of x over 1 over a tangent inverse of what? X over a. The a can be 1. The a can be any number at all. The a can be any number at all. But when it is 1 over x squared plus a squared, to make what you are integrating suit the formula, we just rewrite this one so that the a squared can be seen here. So that this one will be what? Root 2 all squared. So that the tangent inverse, it will suit the tangent inverse what? Approach. But if you forget the formula, you can use trig approach. You can use what? Trig what? Approach. So I'm just going to show you that one also. I'm just going to show you why the tangent inverse. And it is because this one not being 1, but rather more than 1. Some people find it difficult what? Writing. Okay, if it is 1, it's just tangent inverse of p. But when it is more than 1, they find it difficult writing tangent inverse of that. Okay. So this is our right angle triangle. Our p will come here, and then it's 2. We write as well root 2. And then our theta will come here. And then good. This one you are seeing this, by the other part you didn't see it, and then this one yes you have seen it. Yeah, it's nothing, it's nothing, just this one we already know your Pythagoras theorem, and then you are just good to go. Okay, so this one just nothing. Here our focus is just on this one because we're going to take what? Tangent. When we take sine, it won't help. It will be this over this, very difficult to work on. Cos, this over this. Sec, secant, this over this. Cosecant, this over this, to be something else. So we're just going to take tan. So tan theta is equal to p over root 2. Now p is equal to root 2 tan theta. You see, it's just the same thing as the other part, but just that the other part was what? Tanx, hyperbolic what? Function. Now let's differentiate. The p is equal to root 2 secant theta squared d theta. Okay, so let's put it into the integral. Good. Now let's open the bracket. When you open it, you're just going to get 2 tan theta squared. You see, it's just the same thing as the other part, but just that the other one was what? Tanx, hyperbolic function. Okay, we are going to factor out the 2. Now root 2 over 2 will come out, and to be left with secant theta over tan theta plus 1. This will give us 1. And this one, the answer to this one will give us what? Theta. You see? The same thing, but just different what? Identity. The other part is just the same tangent, but in its hyperbolic form. Okay? So, tan theta is what? We know that tan theta is equal to P over root 2. That is where they find it difficult to solve it. Instead of rewriting when it is more than one, instead of rewriting it to suit the a squared, they find it difficult to do that. That is why I'm showing you this part. And at the end of the answer, I will tell you in brief form when it is more than one what you have to do. Okay? So theta is equal to tangent inverse of P over root 2. What is P? Now when we put theta back, when you put when we replace theta with this, we're just going to get root 2 over 2 tangent inverse of P over root 2. We have to replace P with what we substituted it for. Okay? Good. Now you see P is equal to U minus 1 over U. You see the other part we had, it was U plus 1, and you see this part we have gotten it to be U minus 1 because of what? How we rewrite the denominator. Okay? Alright, so the answer to the integral is what? Root 2 over 2 tangent inverse of U minus 1 over U all over square root of what? 2. This one, when you apply the integral formula, which is what? The 1 over a squared tangent inverse of x over a. When you apply that one, you're going to get 1 over root 2 tangent inverse of U minus 1 over U all over square root of 2. But this root 2 over 2 here is a rationalized form of 1 over root 2. And I had this because I'm showing you how the formula what came by. Okay, so if you watch another video and you see that this part they are getting 1 over root 2, is the same thing as what you are seeing here. When you rationalize 1 over root 2, I'm just going to get root 2 over 2. And this one, if you change it back, I'm just going to get the same thing as 1 over root 2 times root 2 times root 2. 2 over 2 root 2. 2 will cancel out with 2. And you're just going to get 1 over root 2. Okay? Here you can still choose to rationalize and you are good to go. If you don't, you just rationalize only this part and then you just leave this part and you are good to go. If you use the formula, you will not end up getting this. But if you try to prove the formula, you end up getting this, which is the same thing as when you use the formula. It's the same. It is equal. I would say it is equivalent, but the value is the same. It is equivalent because when you use the formula, you get 1 over root 2. But when you prove the formula, you get it to be root 2 over 2. Which, if you want to convert it back to suit the formula, you have to re-rationalize the numerator. But I'm not going to do that because actually when the denominator is in the form of what? Radical, we rationalize. Somebody may say, why didn't you rationalize this part? I just that because we are taking this one as the function, I just decided to leave it as it is. I just forget this part. Here rationalizing this root 2 multiply blah blah is going to be a whole lot. Actually, we are dealing with what? Square root. And here is just another square root here, so it's going to be something else. That's why I just leave this portion unrationalized. Okay? Alright, So I didn't write the other one, which is u minus 1 over u all squared plus 2, because that wasn't the original question. We did that just to help us solve the problem. So this one means when you have something like this, it is equal to this one. And when you are showing the workings, that is where the rewriting aspect will what come in. Okay, good. So this one is equal to root 2 over 2 or 1 over root 2 tangent inverse of u minus 1 over all u all over square root of 2. I'm not bringing the plus c because we are not done. It was what? We splitted two things. So we have to put the two answers together before we can bring what? The plus c. Okay? So add a and b. I'm just going to add a and b. With the a and b, you remember for the a part, I told you that we had two ways. And the two ways we had two answers. So I'm just going to show you all of the two answers. So first one, if you go for the hyperbolic function approach, this is what you are going to get. And also when you go for the logarithm approach, what you are going to get. So this is what you are going to get when you go for the hyperbolic function approach. This one too, you can bring this one first minus this. It's just the same thing. Somebody will write it in this way, or maybe this one minus this. They are all what? The same. Okay, guys? Yeah, it's very long, but it's because I want to show you everything. When you understand it, I think it can even take you just 10 minutes just to solve this integral for square root of what x, because you know what you are doing and you will be taking out some what steps. Alright, good. So either this one, or when you use the natural log approach, 1 over 2 root 2 natural log absolute value of this over this plus root 2 over 2 tangent inverse of u minus 1 over u all over all root 2. Here you can choose to rationalize the denominator, but you see, all of the answers that I've been got, all the answers that I had. You see, this one I had it in a rationalized form. This one too, I had it in a rationalized form. But this one I had it was unrationalized. So that is the difference. When you prove the formulas, you may sometimes get them what? Rationalized. But if you don't prove the formulas and just apply the formula directly, you will get it what? Unrationalized. So this one, if you want this one to match this one, you have to rationalize. But if you don't rationalize, this is what you are going to get. So I will not rationalize this one, because just to show you that if you don't rationalize it, this is what you are going to get, and if you rationalize it, this is what you are going to get. Okay, when we rationalize 1 over root 2, this is what you are going to get. And then when we don't rationalize 1 over root 2, we are going to get 1 over root 2. But this one, when we rationalize it, we will get it as root 2 over 4. Root 2 over 4. You know, this times 1 will give us root 2 over 2 root 2 times root 2 give us 2 times 2, which is 4. Okay, so if I rationalize this one, all of them will be in the rationalized form to be something else. So that if you are working on your own and if you don't get a rationalized form for your answer, you might think you are wrong. So I'm just going to leave this one as it is, just to remind you that sometimes if you prove the formulas, you get some of them to be rationalized, and if you don't prove the formulas and you use it directly, you will get what? The unrationalized zone. So this one will remind you of what? Using the formulas directly to get the unrationalized zone, and then these ones, I mean this and then this, will remind you of what? When you prove the formulas. Okay, but at the end of the day, they are all what? The same. Even when you use a particular value and then you replace u with them and then you point it on your calculus, the answer that this one will give you is going to be the same thing as well. The answer that this one is going to give you. Okay, when you rationalize this one and you punch it, the same answer as when you don't rationalize and you punch it, the same answer. Okay guys, all right. So when you add a and b, it is equal to either root 2 minus root 2 over 2 tanx inverse of u plus 1 over u all over square root of 2 plus root 2 over 2 tangent inverse of u minus 1 over whole u all over whole root 2, or this one. All right. So guys, integral of square root of tangent x dx is equal to minus root 2 over 2 tanx inverse of u plus 1 over u all over root 2, or minus 1 over root 2 tanx inverse of u plus 1 over u all over square root of 2 plus either 1 over root 2 or root 2 over 2 tangent inverse of u minus 1 over u all over square root of 2, or integral of square root of tangent x is equal to, when you use this one is from the hyperbolic function approach. When you use the hyperbolic function approach for the other part, when you split it, this is what you are going to get for it, plus this one. And then this, as for the other part, both of them, you're going to get the same thing. But for the first part, a part, because of how we had it to be, we had two ways. We have to work it in two ways. That is the natural log and the hyperbolic function approach. Okay, so from the hyperbolic function approach, this is the answer to this integral question. And when you use natural log, that is the answer to this integral question, the same thing. And when you make it definite integral, you are just going to get the same answer when you use this answer or this answer. Okay, good. But in our next video, to prove that either this or this is the answer to this integral question, we are going to differentiate these answers that we had to this integral question. That's what we are going to do. And I'm going to do that because of the workings and some of the things that we did. I'm just going to do that just to clarify your understanding that no matter the workings that we did to get our answers, when we differentiate it, we are just going to get the original question back. All right, so the answer to integral of square root of tangent x dx is equal to this one or this one. Now we are done with the square root. You see how long it has taken us. Though if you are working as an exercise or assignment or maybe exams, it won't take us all that long. But because I want to show you everything, because we are maybe you say first time of learning it, that is why it has taken us such a little bit long. Okay, now that you have gotten the understanding, as I'm hoping, I don't think when you are solving this same problem, it will take you more than 10 minutes. Yeah, I don't think so. If you don't get the understand, that is where you're going to spend more time thinking of how to go by. But now that you have gotten it, I don't think you're going to spend more than maybe less than 10 minutes. You'll be able to solve this problem, because you will not waste time showing the marker everything. All right, so that is the answer to this integral question. Now let's move on to the other part. Hey, somebody say hey. Yeah, I said I decided to show you both. I just want to show you both so that you will know the difference in solving both of them. You know the difference in solving both of them. Yeah, if I will let you see this one, later bring the other one, you get confused. You don't know the difference. But I want to show you the difference in solving both of them. The approaches, are they the same? Cube and squares, when you are dealing with them, the approach, are they the same? How we deal with this, is it going to be the same thing as how we deal with the other one? How we are going to deal with the other one? Well, it's going to find out. Okay, so let's move on to integral of what? Cube root of tangent x. Hi, I know it's going to be very long, but you guys don't just get bored. Just make sure you watch it to the very end, just to know the difference, just to know how to work such questions, or how to deal with what integral of that nature. You know, when if you are able to get a difference and know the ways of working them, solving other integral problems will not be very difficult, will not be a problem, because the way this one will force you to think, those problems will be very simple, because you have been forced to develop your critical thinking skill from a particular integral approach. So thinking to come out with a particular solution to integral problem that you are working on will not be a problem. Okay, now let's move on to the other one. Don't just get bored. Okay, you can pause it and then maybe relax, and later on come and then watch it. It's very entertaining. It's fun. You know, math is fun. You know, yeah, math is fun. Yeah. And I hope you have never even tried integrating something like this. We have tried tangent. You can also try sine or maybe cosine. Who knows? And see what you are going to get. When you get stuck, you come and watch, and then you think to find a way, or maybe you leave it in the comment section and we sort you out. Or maybe we share ideas and then we do it together. What do you think? Well, you try that one also and let me know what you are going to get in the comment section. But I'm not going to promise you that I'm going to do a video on that for you. No, I'm not going to say that. Alright, now let's move on to the other one. Alright. Oh, sorry guys. Sorry. The answer that we had was in the u word. Okay, so we have to go back to the x word, and as you can see, as you saw, the other part was tangent x, and the answers were tangent inverse of u. So we have to take everything back to the x word. So the answer that you saw before this part is what? The answer in the u word. So if you want to get the answer in our x word, we have to replace what we substituted the u for. Okay, but so let's change everything back to the x word before we move on to the other one. I forgot, if you forgive me on that. Okay, all right. So going back to the x word, u is equal to what? Square root of what? Tangent x. So wherever we see u, you just put what? Square root of what? Tangent x there. Alright. So this one in the x word is equal to, as I said, minus a plus b the same thing as b minus a. Okay, so in the x world the answer is equal to either 1 over root 2 or root 2 over 2 tangent inverse of, it was u plus, it was u minus 1 over u, right? So what is u? That is square root of tangent x. So here is square root of tangent x minus I didn't bring space here, you forgive me on that, minus 1 over square root of what? Tangent x all over square root of 2 minus root 2 over 2 tan inverse of square root of tangent x plus 1 over square root of what? Tan x all over square root of 2. And mind you, 1 over square root of tangent x, 1 over tan x is equal to cot s. It's equal to cotangent. So 1 over square root of tan x is equal to what? You can write it as cot square root of cotangent. Sorry, you can write it as a square root of what? Cot x. Okay, so you can replace this one with what? Square root of what? Cot x. If you don't want that, then you leave it as you are seeing here. Okay, so or either this one, or when you use the natural log approach, this one is equal to 1 over 2 root 2 natural log absolute value of, it was u squared. When we square here, when we square both sides, u squared is will be equal to tangent x. So u squared will give us what? Tangent x here minus, it was u root 2. So u is what? Tangent. So tangent square root of tangent x times square root of 2 give us what? From multiplication law of radicals, we just multiply what is inside. So this is going to be square root of what? 2 tan x. 2 tan x. Okay, so plus 1 all over the same thing is here, just that here it was minus and here is plus. Okay, and then tangent inverse of square root of tan x minus 1 over square root of tan x all over square root of 2 plus c. You see the other part, we didn't see c there, so that one could have even drawn my attention, but I was I'm sorry for what I said the other part. So the answer to this integral question is this one or this one plus c. You can choose to add. If you choose this one as your answer, then you add plus c, and then if you choose this one also as your answer, then you add what? Plus c, but don't choose both. This one and then this one, just choose one. But in general, from most of the videos that you have been watching, they will not show you this part. They will only show you the hyperbolic own, which is what? This one. So they will show you this part, so this one will not come. So if you go for the natural log, this is how you are going to get it to be, and then just pick this one, then you are good to go. Okay, so this one is equal to the whole of this or this plus c. All right, so that is the answer in the x world. What do you think? Yeah, it's very nice. Very cool. Yeah. Should we stop? No, I said we want to know the difference. So now let's move on to the cube root also. But the question is that one also going to take us such long as this one took us? Well, unless we start working it out. So without wasting time, let's move on to the cube root of tangent x. The square root one was fun. It wasn't that easy. Rewriting, doing this. But the question is, though we are going to work it out, but the question is, are we going to use the same approaches, or how we worked the square root on out? Are we going to use the same thing here? Well, that is why I decided to show you both. Okay, so with this one, I'm not going to waste any time, so let's start our solution. And remember, initially I said that we are going to solve both problems using what? Use substitution approach. Use sub is what we are using. All other approaches, all other methods that we are using is just to help us minimize the difficultness of the problem, just to reduce it to what we know, as we did for the other part. The other part, we doing those rewrite blah blah something help us to reach where we can use formulas, formulas to solve. With this one, when we use power rule formula, it won't work. Partial fractions, it won't work. Integrating apart, that's going to worsen everything. Yeah. So the only approach that we can work out for us is what? The use up approach. Okay. Now let's start. Alright. But how is the use up going to be done? So that is the reason why I said I'm showing you both. So please, I know you like math, so just take your time and watch it, and you see that at the end of the day, this video is a little bit different from what you have been watching on tangent, and then square root of tangent, and then cube root of what? Tangent. Yeah, the same approach, but watch how you work it out. You see that this one's a little bit different. It's not all that different. The only difference is that I decided to show you all solutions. I decided to show you everything. Yeah, I decided to show you everything. That is the only difference. Okay, and maybe combining both of them at the same time. Okay, all right. So use substitution. We are just going to let u be equal to, as we did for the other part, we let u be equal to square root of tangent x. So here we are going to let u be equal to cube root of what? Tangent x. So you see the same thing. You see, but just that the other one was square and this one is what? Cube root. Alright, let's continue. Alright, let's do our substitution. U is equal to cube root of what? Tangent x. The other part, what did we do? We square both sides because it was what? Square root. You see, as we are moving on, you see that what we did in the other part, some of them will be repeating here, but in a different way, because this one is cube and the other part was what? Square. So instead of 2, this one is 3. So where we should have squared, here we will what? Rather cube. Yeah, you rather cube. So very, very confusing, but not all that confusing. Just take your time, and at the end of the day, you see, hey, now we can say metin. You see that you say somebody will just see something like that. Somebody will try using it, but you might be thinking, this one I'm wrong. But the moment when the person comes back to watch the continuation of this video, and he'll be saying, hey, you just say, hey, let me cast a something like that. Yeah, so let's continue. So here we are going to cube both sides. To get this cube root of this tangent x, we have to cube both sides. Put 3 on this, also put 3 here. Good. Now let's differentiate. This one will give us what? 3u squared. 3u squared. And this one will give us what? Secant x squared. Good. Let's find what is going to replace the x. You see, the first part the same approach is also here, but this one is what? 3. Alright, so secant x squared is equal to what? 1 plus what? Tangent x squared. Now, tan x is equal to what? U raised to the power 3. Now when you come here, it is what? Tangent x squared. So we can write this one as what? Tan x all squared, so that we can replace tan with what? U raised to the power 3. Okay? Good. So 3u squared du is equal to u raised to the power 3 bracket close all squared plus 1 dx. Now when you square it, from the laws of indices, a raised to the power m bracket close raised to the power n is equal to a raised to the power m times n. So applying the same thing here, this time this will give us what? 6. Alright, what are we going to do? The same, what did you do for the other part? The same thing. Divide both sides by u raised to the power 6 plus 1. So we divide this one by u raised to the power 6 plus 1. And also divide this one by u raised to the power 6 plus 1. Now in the u world, dx will be equal to 3u squared over u raised to the power 6 plus 1 du. Now we know what is going to replace cube root of tangent x and also dx. So let's completely enter the u world. Good. This one is representing what? The cube root of tangent x, and then this one is this one together with this is representing what? The dx. Multiplication is commutative, so we can either bring this one here and then bring the whole of this, attach the whole of this one to this. The same thing. Alright? Now let's multiply. This times this will give us what? 3u to the power 3. Don't worry, I said 3u to the power 3, but you are seeing 3u squared dot u or times u. Yeah, which is a little, somehow the same thing as this. Yeah. Even when I write 3u to the power 3, I will still, in the next step, write it as this way. So there's no need for me to do it that, but I've just said it for you to know that it is that. But because of what I'm going to do, that is why I've written it was in this way for you. Here it was what? U raised to the power 6 plus 1. But here you are seeing u squared all raised to the power 3 plus 1. Yeah. What we write as 3u cubed all over u raised to the power 6 plus 1 du. Now the question is, how are we going to solve that problem? Let's even put the 3. No, let me maintain the 3 there. You see the other part we had 2, and then we maintain it there. Here, are we also going to maintain the 3 as we did for the other part? Well, you will find out. But first, let's analyze something. When we do it that, u to the power 3 all over u to the power 6 plus 1. How are you going to do that? Should we go by the same approach as to what we did to the other part? When we have u squared over u raised to the power 4 plus 1, we use the u squared to reduce what? The powers. But this one, should we reduce the powers? Here is what? On the numerator's position, we are having u cube, but when it comes to the denominator's position, we are having u to the power 6. So when we factorize it, we're just going to get u cube outside u squared plus 1 over u cube, and then u cube will cancel out with u cube, and then to be left with 3 over u squared plus 1 over the inside going to be left with u cube plus 1 over u cube. Okay, now when we get it to be like this, I'm saying it because of what we had for the other part, or what we did for the other part. Yeah, some of you might maybe ask the person was maybe working this one out by applying what we did for the other part. He might try using that approach, but that's why I'm taking my time to say something about that, and before I come to this one. When we do it like that, the top will become 3 over u cube plus 1 over u cube. But the question is, the other part, when we had u squared plus 1 over u squared, we were able to apply symmetric function to rewrite the denominator, which help us solve the question. But here we are having u cube plus 1 over u cube. What approach should we use to rewrite the denominator? Or should we rewrite the denominator? Or is there any formula? Actually, there's no formula anyway. So if we leave it as that, how are we going to do it? Somebody may think taking the derivative as we did. But when you take the derivative directly from where you are having u cube plus 1 over u cube, it will be something else. So as we did for the other part, we rewrite it, right? So let's find something to rewrite it. A cube plus b cube is equal to what? A plus b multiplied by a squared minus a plus b squared. Someone might think using this approach, but I don't know. Well, when we do that, how are we going to split it into like fractions? When we do that, we've gotten two different brackets. So which of them are we going to differentiate, and which of them are we going to leave behind? So you see, I'm saying this because somebody may try how we solve the first one, the approach that somebody may try the same approach here. So when you use how to factorize cube root, and then you factorize the denominator the second time by using a plus b, and then the other part you use a squared minus ab plus b squared. When you do it this way, partial fractions, when you apply partial fractions, that is going to be something else for you, right? Yeah, that is going to be something else for you. But well, that is going to be something else for you guys. Okay, so you see, you will find it difficult if you apply partial fractions and you opt for quadratic factor. Where we are having a squared plus b squared plus blah blah blah, you put bx plus c, and then you find, and then at the end of the day you solve. All right, maybe that approach will work out for you. I will not say it won't work out. It may or it might work out. Yeah, I'm saying this because of what we did for the other part. Though I didn't, work that approach out, I just stick to this approach. Yeah, but because of the other one, that is why I decided to, say it right here. Okay, so I'll leave that part to you for you to try by using what we did for the other part, just to check if it's going to work out. But I'm sure it might work out, because when you apply partial fractions, maybe, I'm not saying it won't, that's why I'm saying maybe it might work out for you. But here we are going to use what you are seeing here. Okay, so if you want to go by that approach, what I just said is going to be how you go by. Right, now coming back to this one, 3u squared times u. We didn't use the u cube to reduce the powers, or we didn't reduce the powers by factorizing and doing cancellation, but we decided to do it this way. I'm doing it this way because when I do substitution, when I let u be equal to u squared and then differentiate, I'll get 2u, I'll get 2u, or maybe I'll get let's say m, I'll get 2m, and then that u will cancel out with this u, and remember u squared is equal to something, so I can replace it with this, and when we come here it will be left with maybe m cubed plus 1, m cubed plus what? 1. M cubed plus what? 1. And with that m cubed plus 1, you see the other part, when we were analyzing the approach that we used for the other first one, in this area, I said you have to use what? Factorize the denominator by using what? A plus b to bracket a squared minus ab plus or b squared. Yeah. You see, doing this way, we have gotten it to be the same. That is why I said it may or it might work out for you. Okay, so when you do it this way also, you just end up getting the same thing as well. That, so here we are going to let u be equal to square root of what? U. Square root of what? U. Then we differentiate. When we differentiate, we can cancel out this u here, and then we can replace u squared with what we substituted the u squared for. Okay, alright guys, don't worry. Alright, don't worry. So we are going to let w be equal to u squared. W be equal to u squared. Okay, so when we differentiate, we get the w is equal to 2u du. So we divide both sides by 2u. Okay, alright, now let's put them into the integrals. Good. So here is w is equal to u squared. I don't know why that system didn't catch it. I don't know why the system didn't catch. I don't want to go. If I want to go back, the time will be very something else. So yes, take it as it is. W is equal to u squared. Okay. I don't know why the system didn't catch it, but it's w, as you can see, it's w. Okay. So here it was u squared, but w is equal to u squared. Okay. So it is 3w times u all over w raised to the power 3 plus 1 times 1 over 2 u. You are seeing u in the w word because of the cancellation that I'm going to show you. This will cancel out with this, and to be left with what? 1 over 2 times 3w over all w to the power 3 plus 1. Okay, and then alright, you see guys, the other part was 2, and then we maintain the 2 over u squared plus 1 over u squared. But this one, after applying the approach, we have gotten it to be w over w cubed plus 1. And if you go by the same approach for the other part, the other one it will be what? If you choose to reduce the powers, it will be u cubed plus 1 over whole u cubed. And then when you factorize, that is what we are going to do here in the next step. You know, this one, we will bring the 3 out of 2 at the back, because you know the derivative of this one will give us what? 3u squared, 3w squared, 3w squared. So actually, when we maintain the 3, there's no way we can split the 3, even when we add and subtract, let's say u squared from it, as we did for the other part. There's no way we can split the 3 to match anything here. So there we have to, there's no need for us to maintain the 3, they have to bring it out. That's why we brought 3 out of 2 at the back here. You know, it's not the other part where we had 1 in our derivative. Okay, so here we didn't have any 1, and then what we had, there's no way we can split it to suit what is here. Okay, alright, so what are we going to do? Well, when we have something like a cubed plus b cubed, it is equal to a plus b bracket close bracket open a squared minus ab plus what? B squared. You know, when you expand it, I'm just going to get the same thing as what? A cubed plus what? B cubed. So we're just going to factorize this one using what I've just said. So note, a cubed plus b cubed is equal to a plus b, what I just said, a squared minus ab plus what? B squared. If you don't want to use this one, you can also use what? The long division what? Approach. The long division what? Approach. Like you can, when w is equal to minus 1, this one will be 0. So w plus 1, then you divide this one by w plus 1. So it will be w plus 1. This one divided by w plus 1. So w plus 1 will come out, and then the long division symbol, this one will be inside, then you divide. And when you divide, at the end of the day, it's going to get the same thing as what? This. Okay? Good. So we are going to factorize this one using what? This. All right. You see, when we do it this way, it's a little bit easier than, you know, reducing the fraction is another way. You know, the other one, no, to be frank, I didn't work this one out using the same approach as I did for what? The square root on. You know, but as I'm elaborating it or as I'm explaining it, I just thought some of you might try, you know, maybe pause the video, and then after watching the square root on to the very end, pause the video and try to use the same approach to work this one out. And as the person is working it out, he will be encountering similar approaches that we use in what? The other one. So if the person is doing that way, then I have to, you know, say something about that approach in this one on that. If he or she wants to work it out using the same approach, that part, how the person is going to tackle it. Okay, yeah, so if you do it that way, like u cube plus 1 over u cube, and then you will write, so when you write here will be what, u cube plus 1 over u cube, and here will be here will be u plus, 1 over u cube is the same thing as what, 1 over u all cube, right? So here is going to be u plus 1 over u, and then here will be u squared minus 1 over u times u give us 1, so u squared minus 1 plus what, 1 over u all squared, which is what, 1 over u squared. Yeah, something like this. And then you apply the partial fraction. But the question is, when you apply the partial fraction, that is where you will be maybe encountering some difficulty. But I don't think that will be all that difficult, because you have already encountered or gone through difficult calculations. So working difficult problem is not something that should worry you. Okay, good. So here we are going to split this one using partial fraction. But this one, with the partial fraction, we have linear factor, quadratic factor, and then repeated factor. And with this one, we're just going to use the quadratic factor because of this one, because this one we cannot further factorize this one. Or can you? This one will be half-half. That is not be possible. But if we can manage to further factorize this one, then we will use the linear factor. Then you get about 3 fractions. But because this one is not factorizable, it is going to use the quadratic factor. So the quadratic factor will be on what? This one. Okay? Alright guys, I know I just take the time and realize that it's time is all gone, but as I said, just let's waste the time and learn something here. When we learn something, and at the end of the day, let's waste the time and learn something. When we got it, I don't think when we are dealing with it we will waste much time on it. If you waste time and learn something, you one day benefit from it. One day benefit from it. Yeah, when you get something like square root of sin s and you are solving it, because you have already learned how to integrate square root of tangent s, I don't think it will be maybe all that a headache problem for you. Yeah, so let's at least waste the time and learn something new from this one, which will help us in some time to come. Okay, good. So as I said, we are going to apply the quadratic factor approach. And with the quadratic factor, where we are having the power 2, it's where you put the quadratic factor. This one is linear, a over w plus 1. Yeah, okay. But here, because we are having not because we are having w squared minus w plus 1. No, but because we are having this power 2 here, that is the reason why we wrote the numerator as well, bw plus what, c. Wherever you see the power 2, if it is not in a bracket or squared, but it is rather in a bracket raised to the power 2 minus something, then we use the quadratic factor approach. Okay guys, good. So bw plus c, and it's all because of what, this power 2, this power 2. This one is dw, not dx. I don't know why my system is not making these errors, but just put in your mind that it's dw, not x. Okay, because we just enter what, the w word. So you just make sure you correct this mistake. Okay, it's a mistake, not x but rather w. Okay, now from the other one, before we split it to this session, it was what, the numerator was what, w. So we're going to equate w to the product of this and this plus this and then this. Good. Now we are going to find the value of a, b, and then c by putting w equal to certain values. And remember the other part, I said we normally do that by looking at the figures in the what, equation. Here the figure here is what, 1, and also here is what, 1. They are all positive. So first, using the cover up proof, when we put w is equal to minus 1, here will be 0. 0 times the whole of this will be what, 0, and then we can get a. And when we also put w is equal to positive 1, here will be minus 1. Okay, that one we have to write an equation, but I still work out. And also when we put w is equal to 0, okay, when we get 1, getting the other won't be a problem. So first, let's put w is equal to minus 1 so that we can get the other one. So that the next one, when we put w is equal to something and then we get equation, we can replace the value for the other one and then find the other one. All right. Good. So here will be 0. 0 times the whole of this will be what, 0. So you're gonna get minus 1 is equal to what, 3a. So a is equal to minus 1 out of 3. Now let's put w is equal to 0. Good. When w is equal to 0, here will give us 1. B times w will be what? B times 0 will be what? 0. So here will be c. And then here will be a. So it will be 0 is equal to a plus c. But we know the value for a. A is what? Minus 1 out of 3. You see? So we can put minus 1 out of 3 here and then find c. Okay? Alright? So we just bring this one to this side and c will be equal to 1 out of 3. Good. Now let's put w is equal to 1. Now here 1 squared plus 1 will be 0, and then here will give us a, here will give us b plus c, here will give us 2. So 2 times b plus will give us what? 2b plus 2c. So actually we are going to get 1 is equal to a plus 2b plus what? 2c. We know the value for a, we also know the value for what? C. So getting b will not be what? A problem. So let's replace a and c with their what? Values. Alright. minus 1 over 3 plus 2 over 3 will give us what? The same denominator. So minus 1 plus 2 give us what? 1. So 1 is equal to 1 over 3 plus 2b. Now we'll just subtract this one from this. Good. 3 times 1 will give us what? 3 minus 1 will give us what? 2. So 2 over 3 is equal to 2b. When we divide both sides by 2, we divide this one by 2. That 2 come and multiply this, making it 6. And 2 over 6 is what? 1 over 3. So b is equal to 1 out of 3. 1 out of 3. Now we have gotten the values for what? A, B, and C. And with A we had minus 1 over 3, C 1 over 3, and then B 1 out of 3. Okay, so let's replace them in the integrals. Good. So here 1 over 3, here 1 over 3, here 1 over 3. So what are we going to do? We can factor 1 over 3 out. And when we do that, here is what? Minus. When we do that, this one will be minus 1 over W plus what? 1. And it's the same thing as what? We can bring this one and then subtract this one from it. So it will be 1 over W squared minus W plus 1 minus 1 over W plus 1. When we bring the 1 over 3 outside here, 1 over 3 times 3 over 2 will give us what? 1 over 2. Why? Because 3 will cancel out with this 3 here, and it will be left with what? 1 out of 2. Alright, so what are we going to do? Here, when we factor out the 3, this one is going to be left with what? W plus 1. So that is the reason why here is what? W plus 1. Yeah. You see, I'm moving a little bit fast for this one. Yeah. Oh, cool. So cool. Here we are going to split. And remember I told you that we normally split them when each of them to work on requires a little bit what? Workings. To solve this one is we have to, work, do a little bit. We have to do some, few calculations before we can get answer to this one. As for this one, we only easily know answer to this one. But just natural log, absolute value of this. But this one, we cannot say the answer is just natural log. We do our other workings before we can get our answer. Okay, so we're just going to split. And this minus half here is affecting this and this. So when we split, this minus half will affect this and also affect this. Okay, good. Sometimes we move fast and sometimes we move slow. Yeah, I normally do that because when the next step is what we all know, or something that is not all that unique or that different. It's just an usual thing. Yeah, that was just by the way. Now let's continue. So we're going to start with this one. After getting answer for this, then we will come and solve this one. After that, we just put our two answers together as usual. You see, the other one we splitted and we put two answers together. This one too, we have splitted and we are going to we have splitted and we are going to solve, and at the end of the day we just put the two answers together. You see? Yeah, but that does not mean the approaches are all the same. So just watch it to the very end and you know what the difference. Alright, so as usual we're just going to call this one A and then we'll call this one B. Now let's start with what? A. So integrating A. what are we going to do? W plus 1 over W squared minus W plus 1. Well, remember the other part, we write some, we did substitution, and then we were good to go. With this, when we differentiate this, now let's try the approach. When we differentiate this, we will get 2W minus 1, which is not the same thing as here. Assuming this one is 2. Assuming this here was 2W plus 2, then substitution will just work and then we are just good to go. But because this one is W plus 1, when we differentiate this denominator, it will not work out here for us. So this is what we are going to do. We are going to complete the squares. We cannot factorize this one, so we are just going to complete the squares. You know, when we complete the squares, I think it will help us solve the problem. Okay, so let's try completing the squares. Partial fraction will not, trig substitution will not work out for here for us. So the only way is to complete the squares. Okay, so the coefficient of W is what? 1. So we will divide the 1 by 2, square it, and add and subtract from this one. The reason is that when you complete the squares, when you add the square of coefficient of W to both sides to this one, it helps you factorize this one. Yeah, it helps you factorize this expression here. Okay, good. But it won't be the normal factorization that we know. Yeah, it won't be like that. It won't be like that. It will help you factorize, but it will not be like the normal factorization that we know. It will factorize some portion and some portion will be left over. But when you expand the factorized portion and you add the other portion, you just get this one back. Okay, so we're just going to add minus half all squared. You're just going to add half of coefficient of what? W, and then we also subtract from this expression. Okay, good. Now when you are completing the squares, first make sure the coefficient of W x is what? 1. If the coefficient is not 1, make sure it is what? 1. Here it is 1. That is why I directly move on to this place. So if it is not 1, make sure you divide it to make it what? 1. After that, you add and subtract coefficient of what? X, or whatever variable that you are working on. Here is minus 1. So when we divide, you're going to get minus 1 over 2. And then we square it. Here, I'm not going to open the bracket. Here, I'll open it. But now, look at this. W squared minus W plus 1 plus minus 1 over 2 all squared. Now, when you consider this one, we can factorize it because here, this square here, this minus 1 over 2 squared here, when we can factorize this one by just considering those having power 2 on them. Don't consider this one, but only this and then that. Only here alone, this side alone. Okay, so you just write W minus 1 out of 2 all squared. When we do that, and then we expand it, we will just get the whole of this one back, and here will be when we do that and then we expand it, you will just get a particular expression back. Then we will add, after subtracting this one from this, whatever we get, we just add it to it, and when we do that, we're just going to get this one back. Okay, so we're going to factorize this one by grouping this and then this, then we square it. I hope you are getting me, or you are getting confused. This one here, we will subtract the value of this 1 over 4. We will subtract 1 over 4 from this one. So actually the factorization is going to be for this one, and that, w squared minus w plus 1 over 4. When we consider that one, then we factorize. We will get w minus 1 over 2 all squared. And then when we simplify this and then this, whatever we get, when we expand this expression and then we add the result from the subtraction of this and then this, and it's going to get what? This one back. Okay? Good. So here 4 times this one give us 4 minus 1 give us what? 3. Good. So now, though, remember I said we are going to factor, but when you complete the squares, it will help you factorize some portion and some portion unfactorized. Now when you expand this one, we are going to get w squared minus w plus what? 1 out of 4. And 1 out of 4 plus 3 out of 4 will give us what? 1. Which is the same thing as what? W squared minus w plus 1. Okay guys? Good. You see here, we have applied the idea of completing squares. The idea of completing square approach, which has nothing to do with what? Integration. But just that, because it can help us minimize the difficultness of our problem and at the end of the day help us solve it. We just integration just agree, and then because it will just help us solve the problem, we just use it, and the integral will just what? Agree. It got no choice. The most important thing is just to get your answer at the end of the day. Okay, so when you use it and it will help you, the integral will just what? Accept, because at the end of the day, it's just going to lead you to a way that you can use what? A formula. Or just need to get a way that you can use what? A formula. So when the integral realize that the approach that you are going to use will help, it will just accept and it will just help you carry on. Okay, good. So what are you going to do? Well, here, do we have any formula for this? Somebody may be thinking of tangent, but the numerator here is not a figure alone, but rather a variable. And because it is a variable, and because it is what? A variable, taking tangent inverse of the whole thing will not what? Work out. So what are we going to do? Well, can we split w over the whole of this plus 1 over the whole of this? Yeah. But first, let's try something. When we differentiate this, what are you going to get? We will get, let's say when we let p be equal to, get the p is equal to what? The w. And p is what? And p is what? And p will be equal to, when p is equal to w minus half, w will be equal to p plus half. So we can replace this w with p plus half. Okay, now let's do that before we split. Let's find the derivative of this before we split. I think that one will help. You can choose to split right from here and then do your and then work it out, or you can do it as I'm going to do mine. First, let's do let's find the derivative of this first. So we're just going to let v, remember substitution, I'm just going to let v be equal to w minus 1 over 2. You know, when we differentiate, we will get dv guys. Don't worry, just that let me just give you some issue, but don't worry, I'll just correct them as we move on. Okay, so v is equal to w minus 1 over 2. Okay, so here is w not m, so w is equal to v plus half. Now let's differentiate directly from here. So the w is equal to dv. The w is equal to dv. Okay, yeah, so here 1 over 2 plus 1 will give us what? That will give us 3 over 2. Yeah, that will give us what? 3 out of 2. Good. So here, I think here we can split, because when we split it will be, yeah, here it is very easy to split and not confusing. Yeah, it is very, very easy to split as compared to the other one. The other part also you can split, but just that you encounter a little bit difficultness. So let's split. When we are splitting, just the same denominator, so this one over this plus this over this, but make sure you distribute this 1 over 2 across. Good. This one is very, they are all very simple. The answer to this one is very simple. This one is also very simple, but because this variable is here, you know, confusion, this one is just here we're just going to do substitution, and then here we just do some tangent inverse, and we are good to go. But yes, let's work all of them out in bit. Okay, let's work all of them out in bit. So let's start with this one alone. Later on, then we will solve this one alone. Then we put the two answers together for that one where we splitted this one from. Okay, so solving C, I'll call this one C. I'll call this one C. All right, now let's start with C. And so here is substitution. You know, when we differentiate this, we will get 2v, and can cancel out with this. Okay, so substitution, we will let n be equal to v squared plus 3 out of 4. Now dn is equal to 2v dv. Now dv is equal to 1 over 2v dn. Okay, let's put it into the integral. This will cancel out with this, and to be left with 1 over 2n. Now that 1 over 2 will come out, and here will be 1 out of 4, and here will be 1 over n. Now what is the answer to this integral? That is what? 1 out of 4 absolute value of what? Natural log absolute value of what? N. What is n? N is equal to b squared plus 3 out of 4. Okay. Alright. Now let's look at the other part. I'll call that one D. Solving D. Here, we will just bring the whole of this one at the back here. And that will give us what? 3 out of 4. It will multiply this and it will give us what? 3 out of 4. Any formula for this? The answer is yes. Because when you have something like 1 over x squared plus a squared, it is what? The tangent inverse, right? So the answer to this one is just tangent inverse of v over square root of 3 out of 2. Yeah, but yeah, maybe this one might confuse, writing this one, as I said, might confuse. So let's work it out. That is our triangle. V will come here, and then the square root of 3 over 2 will come here, and then here will be our theta. This here will be our theta, right? Now, tan theta is equal to V over square root of 3 out of 2. 3 over 4 can also be written as square root of 3 out of 2. So that when we square it, we will just get 3 out of 4 back. Alright? Now, V is equal to 3 Okay, now let's continue. The V is equal to root 3 over 2 secant squared theta d theta. Alright, now after putting them into the integral in the theta word, that is what we have gotten. Alright, so here root 3 over 2 will come out here, and this times this one will just give us secant squared secant theta squared. And then when you come here, this one, when you square root 3 over 2, you're just going to get 3 over 4, and tan theta will give us what? Tan theta squared. Now when it come out, here it will be 3 root 3 over 8. Remember the other part was what? 2. Right? So 4 times 2 give us what? It was 4. So 4 times 2 give us 8. So what are we going to do here? You're just going to factor out what? The 3 over 4. Let's factor out the 3 over 4. Alright, so we will just bring this one out, but it is 3 over 4 here, so when it come out it will be what? 4 over 3. 4 over 3 because the coefficient of this one is 1, so 1 over this, the 4 will just come up here and it will be 4 over 3. And when it comes out, the 3 will cancel out with 3 and 4 will cancel out with 8 and it will be what? 2. So you get root 3 over 2. Root 3 over 2. And I hope you know why this one is called secant theta squared. This tan theta squared plus 1 is equal to secant theta squared. Okay? So this one will give us what? 1. Yeah, so when you integrate this, you're just going to get what? Theta. So root 3 over 2 times what? Theta. But what is theta? What is theta? We know that tan theta is equal to v over square root of 3 over 2. Square root of 3 over 2. What is theta? Theta is equal to the tangent inverse of 2v over square root of 3. Square root of, v over square root of 3 over 2 is same thing as well. 2v over square root of 3. Okay? Alright. So let's put this one to our answer. So root 3 over 2 times tangent inverse of 2v over square root of 3. Alright, so now that we have gotten answer for C and then D, let's add the two answers together. Okay, so add C and then D. C, this is what we had for C, and then D, this is what we have gotten for D. Alright, here we cannot neither add or subtract, so we just leave it as it is. Okay, alright, but leaving it as it is, we have to go back to the W world. We have to go back to the W world. By going back to the W world, V is equal to W minus 1 out of 2. W minus 1 out of 2. Alright. Here, when we open the bracket, it will be W squared minus W plus 1 out of 4. And 1 out of 4 plus 3 out of 4 give us 1. So this is going to give us the same thing as well. W squared minus W plus 1. Okay. And this one, when you open it, it will be 2W minus 1. 2W minus 1. These two cancel out with this. Good. So this one is the answer in the W world, but this one is not the answer to where we split it. Where we split it, getting A and then B. This one is just the A part, and then we split the A part to get C and then D. So the answer for A alone is what? 1 over 4 natural log absolute value of W squared minus W plus 1 plus square root of 3 over 2 tangent inverse of 2W minus 1 all over the square root of 3. So this one, this was what? A. This is what we called what? A. So this A is equal to the whole of this one. Alright? Good. You see, this one, you see the workings is not all that lengthy as compared to the first one. That though we are not done yet, but as you can see, it's not that lengthy, and the answer that we have gotten is not that. But when we go back to the X word, some of the answers that will be gotten, it will be something else. So but it's not confusing. It's not confusing. You don't worry, you will get it. Got it. Okay. So let's move on. So integrating B, we are done with A. This is the answer for this was integral we named A, and that is the answer to it. So this integral here is equal to, remember we carried the half along, so don't waste another time of multiplying 2 through in order to eliminate this half here. We carry it along, so there is no need for you to eliminate this fraction here. So this fraction together with this is equal to the whole of this. Alright? What is the answer to this one? That is 1 over 2 natural log absolute value of W plus 1. You see, this one, the answer is very simple. So the answer to A is the whole of this, and the answer to B is what? This. So to get the whole answer for integral of cube root of tangent x in the W world, we will just add this and then this together, and we are good to go. Okay, good. So add A and B. Remember, A and B, it was what? Negative. It was what? Negative. Yeah, it was negative. It was rather subtracting rather than what? Adding. This is the A part, and this one is what? The B part. Well, this one here is what? 1 out of 4. We are having, here is 2, 2, and also 2 here. So even when we factor out half, there will still be another half here. So that one will not allow us to write this and this together. Okay, because some of you might try adding this and this together. You know, with the other part where we work the natural log approach out, we have something which is similar to this, and then we apply the law of logarithm to write as a single log. That is natural log of something over something. Right, by here we cannot do that because this one here is 1 out of 4, and this one here is what? 1 out of 2. The other part, we got their coefficient to be the same, so it makes the application of what? The law made the application of the law what? Easier. But this one, because the coefficient of this one is not the same thing as well this one, it will not make it possible unless we decide to, you know, bring this one here from the exponent law of logarithm. This one can be written as well the fourth root of W squared minus W plus 1, and then we write this one as well the square root of W plus 1. When we do it that way, then we can apply the quotient law of what? Logarithm, that is log A over B, which is equal to log A minus log B. So yours, if you want to do it that way, then you have to take fourth root of this and also square root of this. When you do it like that, the coefficient of natural log and the coefficient of natural log of w plus 1 and the coefficient of natural log of 4 w squared minus w plus 1 becomes the same, and by that you will be able to write it as the natural log absolute value of fourth root of this over square root of what? This. Okay, good. But but I'm not going to do it that way. I just put that one across just for clarity, just to clear your understanding that if you want to do it that way, that is how you have to do it. But if you want to leave it as I'm going to do it in this video, then you just do it as I'm going to show you. Alright, let's move on. So this is the answer in the W world, but we have to go back to the X world. But going back to the X world, we first pass through U world and then W world. W world was the world we were able to solve what? The problem. So if you are going back to the X world, the same procedure. We have to first pass through the U world. Okay, so first W is equal to U squared. So you're going to put U squared into these expressions. Good. W is equal to U squared. Here it was W squared. So here will be what? U raised to the power 4. Here it was W. So W is equal to U squared. So here will be what? U squared. And then when you come here, it was W minus 1. So here will be what? U squared. And the same thing is applied here. Alright. Now let's go back to the S word. But X is equal to what? U is equal to what? The cube root of what? Tangent X. This is where we are going to get some headache answers. But with these answers, you see, I'm laughing, Yeah, I don't know if we can check the answer by differentiating. The cubes, the way we are going to get the cubes, is very, 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 headache. Let me say it's headache because after getting our final answer, the cubes is going to be something else, which is far different from the cube that we know. So if you are different, try differentiating, guys. But I'll leave that one to you. But I will not promise you that I will give you the derivative of the answer that we are going to get for the cube root of tangent X. I will not promise you that. But well, if you want to try, you can try. But when you get stuck, you just reach out and then you just solve you. But I'm not promising you the derivative of the answer for the integral of cube root of tangent X, as I did for the other part, which was the square root of tangent X. Okay, I'm not saying this because it is difficult. It is not difficult, but it's not difficult to do. But I'm not promising you that I'm going to do it as I did for the other one. It can be that I'll bring that one also to you in addition to the square root of tangent X on. Yeah, after that one, it's a promise. I'll bring it back to you. I will show you that one. I'll show you that one. But for this one, I'm not promising. You can be I'll do it or I'll not do it. Okay, but if you want to do it, but I'm just trying to tell you what is ahead of you because the cubes are something else. Okay, all right. So let's carry on. Let's completely enter the X word, and you know what I'm talking about. Even the cube root alone of this one, differentiating is not, though it's easy, but what happens when this one is raised to the power 6, and not 6, but raised to the power 2, you see, you are doing A, yeah, it becomes something else. So that is what you are going to see in our next step when we completely enter the X world. Okay, so guys, let's completely enter the X world so that we can get our answer for the integral of cube root of tangent x. Okay, yeah. Yeah, I know it's very, 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 very long. That is why I decided to, um, 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 go fast in solving this one. This one is just, when you compare it to the tangent own, is not that difficult as compared to the tangent own. All right, guys. So when you enter the x world, here is what u raised to the power 4. But mind you, u is equal to what? Cube root of tangent x. So when you come here will be what? Cube root of tangent x all raised to the power 4. So when you open the bracket, it will be tangent x raised to the power 1 over 3 times 4. And that will give us what? 4 over 3. So here will be tangent x raised to the power 4 over 3. Now when you come here, it will be the same thing. Tangent x raised to the power 2 over 3 plus 1. So you see, even differentiating the natural log of cube root of tangent x alone will not be all that easy. But here is the case: we are having cube root of tangent x all raised to the power 4, and it's in this form. So if you want to do it, well, I'll leave it to you, but I'll not promise you. It can be that I will unexpectedly or surprisingly I will show you that one, but I'm not promising you. So if you don't get it from me, you know that I've already draw attention, or I've already notify you. Okay, but if you get it, then well, but if you don't get it, then you know that I did not promise you on that. But as for the tangent on the square root of tangent 2, I'm just going to do that, show you the derivative of that for the answer that we had, because of the some workings, confusing workings that we did. Yeah, because of the workings. But this one, all the workings are clear. There are no confusing workings. Everything is just simple. Okay, but simple mean does not mean when you differentiate this whole thing, I'm just going to get this one back easily. You go through a lot. But that is not the reason why I'm not differentiating. Okay, so I'm not promising you I'm going to give you the derivative of this, but when you get it, you get it. But if you don't, but if you don't, then you know why, you know the reason, you know that I didn't promise you. Okay, so if you don't get it, well, you see the reason. But if you get it, you also see the reason. Okay, all right, let's move on. So the answer in the x word is what? 1 over 4 natural log absolute value of what? Into bracket cube root of tangent x all raised to the power 4. In another way, tangent x raised to the power 4 over 3 minus into bracket cube root of tangent x raised to the power 2 plus 1 plus root 3 over 2 tangent inverse of root 2 into bracket cube root of tangent x all squared minus 1 all over root 3 minus 1 out of 2 natural log absolute value of into bracket cube root of tangent x raised to the power 2 plus 1 plus 1. Okay, guys, let's add our pluses to complete everything. So there is the answer to integral of what? Cube root of tangent x in the x world. Yeah, it's very, very, very it's something else, that is why I decided to show you both, so that you guys will decide for yourself. Okay, all right, so let's continue. All right, so therefore let's end it. Therefore, integral of cube root of tangent is equal to, I'm not reading again, I'm tired. Hey, I'm not reading again, I'm tired. Yeah, I know it's not easy. Just take your time and watch it. If you have any questions, just leave in the comment section, and then I'll just find time and answer. But if I don't get it on time, well, just don't worry. All right. So guys, the answer to integral of cube root of tangent s dx is equal to the whole of this one plus c. Okay, so you see the difference. I'm not going to tell you the difference, but you see that for the square root own, the answer that we had wasn't all that lengthy. We had the answer that we had from the hyperbolic function room, it was just two answers, just short. From the natural log own also, though it was three answers, but we managed to put two together and we got two answers at the end of the day, but still the answer was very simple. But for the cube root own, but the workings that we did, you know, some confusing calculations, change this, do this, this plus this, this plus this, you know, we did a lot of confusing calculations as compared to this one. You see, this one, all that the calculations that we did wasn't all that confusing. We didn't rewrite anything, we didn't just, you know, we didn't, you know, do all that lengthy calculations as compared to the other one. But the answer that we had is what, as compared to the other one, is very lengthy. And the answers are is something else, you know, cube root to the fourth to the power, oh Charlie, it's headache. But one thing is, the other one we had natural log in it and tangent inverse. It's like even I'm giving you similarities and differences. Let me leave that one to you guys for you also to do it. Okay, that is the reason why I do it. I did it. I combine both of it so that you guys can do the difference, or can do the difference or the similarities, or maybe something like that on your own. Okay. Yeah, that is very cool. That is very cool. And forgive me for doing such a very long video for you, but just I want you guys to know the difference between these two integrals. They are not twins. Twins, they are the same. See, let me say unidentical twins. They are unidentical twins because this one is square root and this one is what, cube root. So they are unidentical twins. Okay, so the answer to this integral is just the whole of this one plus c. It's an indefinite integral. Okay, so if you want to differentiate, you can try differentiate the whole of this one. But to be frank, I'll tell you, it won't be all that easy for you. Even dealing with the cube roots alone without any powers, it's not all that easy. But here is the case, you're having another powers on them. It's not all that easy. It won't be all that easy for you guys. That's not the reason why I'm not promising you that it can be, I can surprise you on that. Okay, so if you want to do it, well, I'll leave it to you guys. And if you get stuck at anywhere, then you just let me know, and then we'll just maybe sort you out. But just, you know, the workings. All right. As I said, yeah, it's going. Yeah, it's been a long. If he spent a lot of time. Yeah, you have spent a lot of time. Yeah, you just forgive me for that, but it's because I wanted to show you the difference. Okay, you just take your time, watch it, and then know the difference and know how to approach all of them. Okay, so if you have any question, just leave in the comment section and I'll do my possible best to answer you. And please make sure you don't just watch it like that and then you just we'll make sure you just learn how make sure what you learn, make sure you just apply them, and whatever that we will also say, make sure just apply them. You know, if you do that, it will help you think critically. If you do that, you know, sometimes when you are trying to think critically, it is something that if you don't take care, you won't be able to do it. Because if you cannot solve the problem, you will feel very, very, very lazy to think. You know, when you are thinking and you are not getting any like this one, let me say like this one, where we had the assuming you haven't watched any video on the square root on, and then you want to solve this question, and then you just reach u cube over u to the power 6 plus this, and you are, you know, if you are not fond of thinking, you are not fond of doing that, to be frank and honest, you just end it there and just do this question, you just forget it and forget. And the more you are just throwing it away because of it difficultness, because of this difficultness, it just become part of you, and you will not be able to solve any problem which require critical thinking. Okay, so the motive of this video one is just to help you develop your critical thinking skills, and just to also just to help you develop your critical thinking skills. When you start doing that, though this approach will not work, but just try. If I do it this way, it won't work. What about this? What about it? It's a waste of time, but the moment you do it in these petty ways and you figure out what work out for you, in the next way, the time that you took to come out with the approach which work out for you in a previous problem that you solve, it will not be the same time that you are going to come out with a approach which is going to help solve your current problem, because the mind is used to doing these things. So the moment you start doing it, even when you start the first step, because the mind is used to, it can work it out in very, very a fast way for you. So when you say maybe this approach and this approach won't work, quickly you get to know that this approach will not work, because you are used to. You will not end up doing lengthy workings on the paper or maybe somewhere. All those lengthy workings will be something small in the head, and what will work out, you see, the moment you just try, because the mind is used to, you just figure it out. So you see, but I said this because when you are fond of doing something persistently, it makes you let me say special in that thing. You are fan of drawing, you are fan of singing. The more you are doing it, the more you are becoming special in that. Okay, so guys, I'm not advising you, but just because of this lengthy calculator, that's why I choose to say all these things. So try, and then after watching this, try and then start developing your critical thinking, and I think that one will help you. Not only math, science, chemicals, chemistry, physics. With the physics class, those areas, though they are formulas, but there are sometimes you have to take, titration, then those stuff and other stuff. Yeah, sometimes or some of them that you have to think. When you are giving some, I will not go there. We are doing mathematics. We are not doing chemistry. Yeah. Because if you don't do that, you can't become a doctor. You can't become anything, because the problems that you come across are not problems that are require easily thinking. Though there are ways, but there are some ways. Even the way is there, but you have to think of how to use that way to suit you, or to get the best out of it. Yeah, somebody will use and will get the best, but you also use but will not get the best, all because you didn't use it well. Though the way is there. Okay, so that was just by the way. Forgive me for that. Just that was just by the way. All right. All right, that's it, guys. Please, if you like this video, and I hope you do like this video, because I've just shown you all solutions. I didn't omit anything. All solutions. Okay, so if you like this video, kindly give it a thumbs up, subscribe, and comment. Thanks for watching. I'll see you in another video. Bye for now.